Good morning.
Hi, hello.
Good to see you, Danilo. I should say good afternoon since you're in Italy.
Ciao, Pete. It's great to see you and to be here today for these couple of days. Very interesting presentations on generative edge AI. That's
Yes,
great.
it's our fourth installment. So if folks remember, we started this in spring of 2024. So the Generative Edge AI working group as part of the Edge AI Foundation, and Danilo is the chair of that working group, right? So we're bringing forward kind of the latest and greatest in what's happening in this space. So in generative AI, agentic AI, all that good stuff, right?
Yeah, Pete. Generative edge AI is a super topic we are living and learning and experimenting since a couple of years. I should remember that the topic was started by Davis Sawyer, and
Mm-hmm.
he started the first forum, and then I also followed up. And in all these events, there's been an outstanding contribution from many parties, which means that the topic is very, very alive.
Yes,
And
yes.
and
Yeah, and if you
let
look,
me say,
oh, go ahead.
please. And let me say that I'm really grateful for all the speakers that made their availability in these 2 days. Just consider that we have 9 speakers today and 10 tomorrow, which is a record compared to the other forum. It's really huge. And then we have IDC you will talk with, and
Mm-hmm.
McKinsey tomorrow.
Mm-hmm.
And yeah, that's really hot.
Yeah, no, it's definitely a record breaker on speakers. And so for folks that are viewing here, welcome. And this will all be on YouTube as one big long stream per day, but then we'll chop it up as well. But it's going to be, this is for the attention challenged, these talks, because it's like 15 or 20 minutes a talk. Which is good. So people will kind of get to their point, and but it's a live stream too, so people will be able to ask questions along the way, and we'll have some time for that as well. So people should sort of buckle up, get their coffee refilled, and get ready for a good day of talks on what's happening in the space, right?
Yeah, we try to be very efficient today and tomorrow because of all enthusiastic acceptance from many speakers. So we devoted
Mm-hmm.
15 minutes each, and so please, all the speaker, be very focused on the key messages and the actions you want the community to take. And let me say also another thing, Pete, that this is possible thanks to the steering committee of this working group that I have the privilege to chair. And so let me mention Tinoche Mosenin,
Mm-hmm.
Roberto Morabito, and
Mm-hmm.
Mike Stoffer, and obviously the super person that assists all of us and make this possible is Rosina Alber, and obviously you and Evgeny for the great support. Otherwise, this won't happen. So thanks so much.
Yeah, no, it's definitely a team effort, and I just came back from Taiwan. We had our Taipei event there last week. Had some amazing demos, some interesting generative edge AI demos as well. So hopefully we'll talk about those today. But it's definitely happening.
Unfortunately, I missed it.
Yes, well, and I will apologize in advance to our folks in the Asia time zone where this is not exactly prime time for them. But hopefully they'll see it on the YouTube afterward. But yeah, time zones are tough. Like it's early morning here in the Pacific Northwest. It's late afternoon in Europe, and it's the middle of the night in Asia. So hard to fix that curvature of the Earth thing. But not sure how to fix that. But yeah, no, this is going to be great. So why don't we bring on our first guest and from IDC to kind of have a kind of a high altitude view of what's happening in this space. And then we'll dig into it. Let's see. Let's bring on Rob.
All right.
Good morning, sir.
Hello, Rob.
Good morning. Good morning. How you doing, everybody?
Good. And
Good.
yeah, and Rob, you're calling in from Texas, I believe. So you're
That's correct.
Late morning for you. Not
late morning. Absolutely. No, I'm thrilled to be here. Yes, I'm a research director at IDC, and I work in our cloud and edge group, being an analyst person and covering all that stuff and writing all kinds of papers and talking intelligently to executives.
So give us like kind of, so you're on the front lines here, talking with like real customers about how they're deploying generative AI. And I know we've talked in the past about, generative AI obviously has been in the headlines for a couple of years now, the good, bad, and the ugly. And,
right.
But what we're talking about here is how do we bring generative AI to a more, I don't know if the word controlled environment is, but a more focused environment to do more focused things on edge computing. But what's the temperature out there with edge computing and generative AI? Is there, we're starting to see some inklings of interest?
Just little inklings, I mean, customers are just getting around to the idea of maybe even, like, let's say, without going to the edge, obviously the hyperscalers are sucking most of the auction out of the room when it comes to generative AI. And then you've got the neo clouds, right, who are just GPU clouds. And so that's where most of the action is. I'd say 99% of the action is happening there. Then there's this small movement around the idea of customers. This, you and I've talked about this before, the notion of companies got their own proprietary private data, right, from their employees, their machines, their everything. And they don't necessarily want that data to be up in someone else's large language model for the world to see, right? And so this notion, and I promise I'll get down to the edge here. We're going to make our way to the edge. But kind of that step one is, all right, maybe if the company has the infrastructure capability, and this obviously narrows the list already, the idea of I'm going to download a pre-trained, maybe open source large language model. And for maybe the largest companies, they could afford to have their own kind of infrastructure in their own data centers or co-location facilities, pre-trained. And then the idea, and like anything, is then you've got to do fine tuning, some RAG to kind of train that pre-trained model on your domain specific information about your company, your business, everything you do, so it can work intelligently. Because then whether it's employees talking to it through chat, or if it's agents communicating with it to take care of tasks, that's what it needs. And so that you kind of get this idea of over time having this this enterprise intelligence, enterprise brain that knows everything about your domain. If we start to go smaller than that, and again, it's still really early days, especially when when we're talking about generative AI, because it's so big. That's when you start thinking about like quantization, right? Like it's a lot of us have been doing edge computing for a long time, and we did rules engines, if this then that, all kinds of stuff like that, KPIs. And then we started to do some machine learning at the edge, and with TinyML and other things like that, where it made sense. Obviously, doing generative AI at the edge, depending on which edge you're talking about, is a huge leap, just because they're so much bigger and they require so much more power than maybe a tiny small machine learning model would. And so, generally speaking, I think of that term quantization. I'm going to reduce the precision of a model from maybe 32 bits down to 8 bits or 4 bits, this kind of, and removing unnecessary weights from it, kind of the pruning. You're trying to do everything to make it smaller, right? Something big, make it smaller. How do I get this thing? You've heard the term distillation, knowledge distillation. And so you're tackling that problem from all these angles to get it small enough. And, luckily there's companies that have small models.
Well, it's kind of the hot thing these days is small language models. I'm sure we're going to talk about that in the next couple of days. But,
Oh,
10
yeah.
billion parameters or less seems to be sort of the sweet spot. If you look at the proliferation of language models out there,
Yeah.
we're seeing a lot more small language models. One of the reasons is, training a trillion parameter model is kind of expensive, and
It's kind
is
of a little
only
bit of money there.
like
Yeah.
Sam Altman and one other person can do it. So
Exactly.
people are doing much more focused, and
Right.
more efficient, language models. But so I think what you're saying is there's kind of phases. We start with kind of the big public chat GPT stuff, which we're all familiar with, and unicorn pictures and fake girlfriends and all kinds of important scenarios like that. And then we move to like, well, actually I have private data. Like maybe I have my silicon semiconductor roadmap, or maybe I have some other, data sheets about my products and things. I don't want to put that into the public kind of, language model cloud. And so I'm going to run that more on-prem, near-prem, which we would consider to be edge if it's outside the multi-tenant data center.
Sure.
And then you move into then the next phase is, moving into much more functionally focused deployments of edge models. Actually, just as a quick example, when I was in Taiwan last week, we had Advantech had a pretty cool, it was like a kiosk sign with an avatar person.
Mm-hmm.
And
cool.
It was running a standalone Advantech box with a language model on it that was trained on Edge AI. So we had fed it a bunch of information about the foundation and about Edge AI. And so you could walk up to it and ask it questions about Edge AI, and it would, in an animated way, respond to you in real time. And it was all running. There's no cloud. It was all
right there.
It was all like in the sign. Yeah. So you can imagine those in like an airport kiosk or at the end cap of Home Depot. Every time I go into Home Depot, I'm like, where is the crazy glue, or whatever.
Right.
I want to find one of those people with the orange thing. I can just ask the
exactly. Where are those people with the orange suits? And so it's funny you say. I'm glad you said Advantech, because my experience with the edge, that's where I came from, because I was doing the whole industrial factory thing. And so at least for me, the edge meant an industrial gateway kind of thing, like an Advantech box. Dell made some, HP made some, different companies made those things. And when you have that kind of compute at the edge, that, x86 or ARM, you can put something bigger on there, right? You can put a larger model on that, no doubt about it.
Exactly. And something like I saw some stat, it was something about it, but roughly like a gigabyte of RAM memory per billion parameters ish. So something like that. I mean, we're going to get more efficient than that, but that's not unreasonable to put like 16 gig on a box, or 32 gig on a box like that, and put it out there on the edge. Right.
Because people say, I want to put this thing on my Raspberry Pi. And if you have like a Raspberry Pi 4 or 5 with 8 gig of RAM, then you probably could put a 1 to 3 billion parameter model in there. But you still are going to probably quantize it down to 4 bits, And the speed is another thing. And so, especially on a Pi, if you're okay with like 1 to 5 tokens per second, it's like when a bunch of us downloaded DeepSeek onto our laptops and started running it, or someone said, build a gamer PC and then get the whole 700 whatever gig of RAM in memory, but it was still like 1 token per second kind of thing.
Right.
And so so the industrial stuff you're talking about, and using those in the store, like you said, with the kiosk, they have a lot more horsepower. Then you get down to that Raspberry Pi size. And then but then if we're talking about the really small, microcontrollers, that's where it starts to get kind of tricky, right? And the problem is, we're talking about kilobytes of memory versus megabytes or gigabytes, right?
And so I don't think we've broken that barrier yet, but
and so whether we're talking about it's not that I don't love microcontrollers, but it's just fitting the RAM, the data, the space. They just don't have. It's not even close, right? And so I think you could do it on a Pi with 8 gig of RAM, but you're probably better off with those other edge computers. And then you're right. And then that bigger edge, which looks like servers, but it's not in a data center.
Right.
Kind of like when I was at Hitachi doing Lumada, we made sure that we could run the whole thing on a factory floor. And so we
Right.
roll in a rack of servers, and you're right, they're running
Right.
at the edge, they're not in a data center, and they needed that millisecond response time.
Right. That sort of feels like that's the frontier right now that people are really thinking about deploying. And then we get into more of the kind of heavier device edge, like the kiosky kind of thing. And then we get into, I mean, we'll see at CES how many talking refrigerators we see out there, but
What?
someone will try it. But then you get it into more of the appliances and stuff, and that's that's out there a little bit. But what we're seeing now, at least, people are building muscle around standalone multi-billion parameter models that are doing very useful things, which is a lot of what we're going to be hearing about over the next couple of days. And so that's people
exciting.
think about it in phases of like, okay, super public cloud, my own private language cloud, language model cloud thing, not even a cloud server, and then into the device, and then into the micro device. Maybe that's something that's a little farther out, but
until we just start pumping tons of RAM onto microcontrollers.
And it is right now very RAM bound.
It is RAM bound. You're right.
More than like TOPS bound. And of course, we haven't mentioned phones. I mean, pretty cool edge device. Most of us have one in our pocket,
Absolutely.
unless you live under a rock. And then, and you can run language models, multi-billion parameter language models on those.
On a phone. But when you think about that scenario, whether it's a phone or it's an IoT, a small device, an edge device, or an endpoint, you think of that kind of that hybrid architecture. It is probably the best way it's going to work. If that makes sense. And this sounds like old news. Training the model somewhere else, getting a little one down there for inference. But you're right. Most of the world is sitting there with their phones, talking to Claude or ChatGPT or whoever. And it's a hybrid architecture.
Right.
And so you can imagine when you want to deploy stuff, if I want to deploy stuff in manufacturing or in agriculture or whatever, at least right now, for instance, maybe the best bet for edge AI, generative edge AI, is that kind of hybrid model. I've got APIs back to my cloud or my core. Yes. I always used to get frustrated when people said, you're either at the edge or the cloud. And I was like, well, what if we build some big giant thing that's not in the cloud and it's somewhere else? What do you call that? Is it core?
There's lots of edges out there.
Absolutely. And so I think just like we talk about hybrid cloud these days, it's a very popular thing. I think the hybrid architecture is probably what's going to work best for agentic edge for smaller devices that maybe don't have the horsepower. And so there's API connections or sync connections to a cloud. I can figure out what I can figure out. I can do inference. I can do object detection. I can do classification right here. But if I need to talk to the cloud to get some more love, then I've got an API to do that, something like that.
Yeah. And what's also cool about the phone, and I would say the PC market as well, I mean, these are high volume markets, and so they're providing an opportunity to for people to cut their teeth on generative edge AI technology at scale, which would then make its way into more commercial deployments, right? So I think, like, for example, Qualcomm just introduced kind of industrial versions of a bunch of it's the Dragon Wing stuff, which is derived from Snapdragon. So people that are running on those platforms at scale in phones, those models and code is now it provides them with a scale platform, which has always been a challenge, I think, for a lot of the more commercial deployments is kind of they're small volume but high impact. So now that I think the PC and phone platforms are providing market opportunity for folks to get things deployed.
Absolutely. And it gets that familiarity built up with people who are using this stuff. So it doesn't seem like it just came from another planet all of a sudden.
Yeah. And of course the business aspect, which we haven't talked about much, about running things on your own platform, you eliminate your OpEx costs or radically reduce them. So people don't always realize, like, if every AI workload is running in the cloud, then that's, ka-ching, ka-ching, and every time.
Paying for those tokens, right?
Yikes.
And data egress and all kinds of other stuff. You're right. And so, absolutely, if you can do it on-prem, if you can do it in your data center, do it out the edge with your own gear, that's the way to go. And so go see your friends at Hugging Face or wherever. There's so many models out there that you could download
That's
that
true.
are already trained, and then you can tune them up, right, for your specific use cases.
Exactly. Well, Rob, we are at time.
Okay.
Thank you so much again for your words of wisdom. And let me bring Danilo back on here, but thanks again. And
All right.
we will see you shortly.
Sounds good. Always a pleasure, Pete. Thanks for having me.
Rob. All right.
Thanks, Rob. Thank you.
All right. Good
so, Pete,
context.
It was a great conversation. Fortunately, we need to move forward. There is the next speaker, Thomas Ziereis, Roofline AI. So title is Compiling and Running SLM on Edge. Thanks, Thomas, and the floor is yours.
Thank you for the introduction. Thanks for having me. Hello, everyone. I'm Thomas from Roofline AI, and today I'm going to talk about compiling SLMs to run efficiently on edge devices. But first, a couple of words about the company. So we build an adaptive and retargetable SDK based on a next-gen AI compiler technology. What this means is that our SDK is flexible enough to support basically any kind of model. There we are talking about different kinds of neural network architectures coming from different kinds of frameworks like PyTorch, Onyx, and so on. And then we can compile these models and deploy them on different target hardware, like, for example, CPUs, GPUs, or AI accelerators. We believe that building generative AI products is still painful, and that's where we offer, where our tooling offers a best-in-class performance in terms of deployment speed, going from, let's say, some model on Hugging Face to actually deploying it as an Edge AI product. And particularly what I want to talk about today is about the new challenges that arise when deploying these language models in comparison to like this more traditional one-shot inference models. And first, to categorize these two things, when I'm talking about one-shot inference, I'm talking about something you can see below on the left side, for example, where I would have some image classification model that takes as input some image and then produces some output labels, for example. Now, for this use case, I would mostly have static shapes, meaning like the tensor shapes are fixed. And this applies for the input, but also propagates through the entire network. Maybe I have some dynamic shapes in the batch size. And also, in general, the execution is completely stateless, so I don't require any external state while executing. And then for inference using language models, this is quite different. Let's say on the bottom right, the language model wants to generate the sentence, "the cat is cute." This wouldn't be possible with like a single forward pass of the network. And instead, it would require many iterations, and also not only many iterations, but it would also have to read and write from a mutable cache or a mutable state that is shared across these iterations. And also, the input of these language models is usually very dynamic, so we also have to be able to handle dynamic shapes in the compiler. And to go into more detail of how the language model inference actually looks like, which is usually when we are talking about conditional generation, I would have an input prompt, which can be this quantization can, which we can see in the bottom, which would then be fed into the through the network, where the network would write some internal state into this KV cache object and then produce one output token. And this phase, in general, or like this first iteration of this language model, we usually refer to as the prefill phase of the model. And then after this, the first output token I produce, I would feed into the second iteration, and the second iteration would then again write and read from the cache and produce another token. And this process of receiving one token, producing one token, would be repeated many, many times until the full text is completed. And this is what we refer to as the decoding phase of the model. And then in general, there are two key challenges that arise here that are very new and specific to these language models. The first thing is that we cannot control basically what shape the input will be, because the input can be basically any text that can be of arbitrary length that the user provides. And the second challenge is to correctly handle this mutable state, and this is in particular relevant for the decoding phase. Then let's first talk about the first challenge, which are these dynamic shapes of the prefill stage. Why do they even arise? So as discussed, usually I have some prompt of the user, which could be how a language model generates text. This would be the prompt. This would then get divided into subwords, basically, and these subwords would then be tokenized. And this process of tokenization is basically the process of assigning an integer ID to every one of these subwords. Then what we have to account for here is that at compile time, we neither know how long the input prompt of the user will be, and we also don't know to how many tokens in the end this text will be tokenized to. And so in the end, we would have as input this arbitrarily sized vector of integer IDs. And the key observation we have to make here is that this shape of this input tensor propagates through the entire network. So many operations in this in language models are matrix multiplications. And this means that I have matrix multiplications with dynamic shapes basically all over the network because this dynamic shape is dependent on the size of the input. And now for generating efficient code for this, we have this fundamental mismatch that we don't know what the shape is, but we have very fixed hardware instructions we might want to target that are completely static. What you can imagine here is that let's say one of the inputs, so if I have a text that would be tokenized to 30 tokens, I would have somewhere in the model a matrix multiplication, for example, where one input would be a 30 by 16 tensor, for example. And then let's say I want to target some NVIDIA GPU that has some fixed size tensor units I want to use. Here, this I can do basically, I can fit one tensor instruction into my tensor here, process 16 by 16 square of my input, and then I would have another 14 by 16 square left. Now the problem is here that I cannot use the same tensor instruction again, because then I would basically read out of bounds and not produce correct results. And generally, this is not a new problem. This is also did also arise in the past, and there also exist some traditional solutions to handle this. One of this is to do padding, so where we would basically fill this input tensor with some neutral element to make it to some shape we can nicely handle with our hardware instructions. So here what we could do, for example, is pad it to a 32 by 16 tensor, so we can nicely fit to 16 by 16 hardware instructions. This in general can lead to performance penalties because this might require extra kernel launches, extra allocations, and memory transfers. Then another way we could handle this is through peeling. Peeling would basically be the process of taking this leftover tile that's 14 by 16 in shape and process this using some other instructions, some maybe vector instructions that now fit, or scalar ones. The thing is, this works well on loops, so this is a good technique to do on CPUs, but generally doesn't really work well on GPUs. And then the last option we have here is masking, where basically the hardware vendor would provide some instructions that can just handle basically this overlap we see here, The issue is that this might not even exist on some hardware, and even if it exists, it might still lead to performance penalties when actually using it. So the nice thing we can do with language models is that instead of using this per operation techniques, which I just proposed, is that we instead pad the input to be always aligned to some constant we can then later use in the code generation. So what this means in particular is here, let's say we have like 30 input tokens, and we could then instead just pad the input tokens to 32. This dimension would then propagate through the entire network. So I could use these tensor instructions through the entire network, and I wouldn't have to bother about doing any like additional operation-based padding or peeling. The issue here is only doing this input padding alone is not enough. We also have to communicate this information, basically, where we can say we will always pad it to a multiple of 32. We have to communicate this somehow to the compiler, and we can do this through constrained dynamic shapes. So instead of saying, oh, we have an input that is arbitrary size, we can just say the input is not completely arbitrary, but it has to follow certain rules, which would be here, for example, okay, the input length always has to be larger than 0, less than 2048, and always divisible by 32. And then we can use this fact that it will always be divisible by 32 to just emit our tensor instructions and get good performance. And what this means, basically directly for us, we measured this on an NVIDIA GPU where we did, where this like we get 100% performance using this input padding with this constrained dynamic shapes. In comparison to padding, this is 2 times faster, and in comparison to not doing any of the techniques I proposed, this is 4 times faster. And then that's basically about it, about the prefill phase. And now we will take a look at the decoding phase. So here, just to recall, what we are doing here is we always will receive 1 token and produce 1 output token, and we have like this many KV cache updates. And one thing we have to notice here, so what I displayed below is just like some chunk of how like a traditional language model looks like, where I have these QKV projections, which would then be just matrix multiplications. And in particular, for the decoding stage, there wouldn't be matrix multiplications, and instead vector matrix multiplication, which are memory bound. So they are generally easy to handle, so we don't have to worry about them much anymore in the decoding stage. And what we instead have to take more care about is about the attention computation that comes afterwards, which you can see to the right side. And an important part here is also to correctly handle the updating to the KV cache, which I will talk about more now. And so in particular, what is important about this, or what we can consider about the KV cache is where we place it. So one way to do it, which is like the most common way to do it, is to just provide this like cache tensors as input arguments, where the model then during inference can freely read and write to. This has the advantage that I don't have to fix the sequence or my maximum sequence length of the model during compile time, and can instead postpone this decision to whenever I actually allocate this cache tensors. However, this also has some disadvantages. And in particular, the alternative to providing this as function arguments is making the KV cache as total internal state of the model. So don't expose it at all to the outside world, basically. The nice thing about this, if it's like completely an internal structure of the model, we are free to do much more optimizations in the compiler, which we couldn't do if we would have them as external arguments, since we, for example, wouldn't be able to decide which data layout to use. And then another thing we also care very much about is heterogeneous execution. So if you think about the use case of having some accelerator that's restricted in the amount of memory it can use. We can, if we have like the KV cache's internal state, we can basically have a smart partitioning algorithm that can also put parts of the KV cache, maybe not for all layers, only how much as it fits on the accelerator or on the memory the accelerator can access. And this is also something that wouldn't be possible if we provide the cache as function arguments. And then the way we use this, or way this is used at Roofline, is that we integrate this and many other optimizations into a full pipeline to deploy cutting-edge LLMs to the edge. And one example would be basically deploying various kinds of models from Hugging Face through our compiler, where we would, like discussed, use some of the optimizations we discussed here and other ones to have like a deployable artifact. And we also then provide some wrappers over basically our model and the runtime to use it with an OpenAI style API, for example, in some small web server. And then also just some practical examples of how we actually managed to use this. We were able to compile, for example, a Gemma-free 4 billion vision language model very shortly after it was released. And what you can see on the right is just some demo of it, where we provided an image and asked it in the prompt to describe the image. And for this task, we achieved 9 times better performance than Torch, running on a Qualcomm Snapdragon laptop. And another demo I have here is heterogeneous execution. Here we just have a MacBook where we execute a large language model or like a small language model. We execute, we generate text with it. And as you can see in the utilization part graph below, is that during decoding, we offload some of the work during decoding to the GPU. That's it from it. That's it from me. Thank you for listening, and I am open for questions.
Thank you so much, and for your really exciting presentation. Let's check if there are comments or questions from the chat. I see one from a person. Is peeling padding similar to delayed road operation in computer vision?
Sorry, my sound was a little bit quiet. Could you repeat it?
Yeah. Is peeling padding similar to delayed road operation in computer vision?
So I'm not super familiar with computer vision, but I think they are quite different things. So I think usually for computer vision or like for convolutions, I think is the question. You also have padding, and the padding I proposed here is also like similar in some way, but I think like peeling would be a different technique. It wouldn't really change what the operator does. It's just an implementation detail, basically. I hope this answers the question.
Hope so. Next is there is Subham, which would like to know which board and the model size you used.
So for the benchmarks we have before here, if they, for example, here the CPU benchmarks are run on a MacBook M4, and it was a Qwen 3 0.6 billion, and here it was running on an NVIDIA GPU on a RTX 3070 and also Qwen 3 0.6 billion.
Okay. Can you just comment the complexity difference between the prefill and the coding in your studies?
Complexity in terms of how hard it is like as a compiler to get it right, to get good performance, or like in general,
You
like
You mentioned that there are two phases, prefill and decoding, right?
Yeah.
And in decoding, you have a lot of KV cache interactions. While prefill decoding seems quite serial, right? And so I just wanted to know if in your experimentation, in your implementation, the typical partitioning in terms of complexity between these stages optimized or less.
Yeah. So in general, I think like the deep decoding phase is like easier because it only deals with like this static shapes, because I always have one input, one output. But then again, the decoding phase, I repeat it many, many times. So it's also in that sense a little bit more performance critical, and even like very small things actually matter here. And then on the other side, for the prefill phase, you have like this dynamic shapes, which I discussed, which are also like challenging on its own. So I think it's hard to say if like one is more challenging over the other. But yeah, I guess in general, I would say it's the prefill phase.
Okay. So Subham has another question. What's the memory capability of the board on CPU embedded? Since he is working on Google Coral, I think, where he can upload only 8 megabytes of model on that. Maybe these are too few, right?
Okay, yeah. So the model I'm running here, this would be like 600 million parameters.
Yeah.
So even if it would be like quantized to, let's say, 4-bit, it would still probably, including the cache in some state, like at least take like, let's say 400 megabytes of size. So this is, even though like the model I used for demo here is quite small, yeah, 3 to 400 megabytes is still then quite a lot larger than the 8 megabytes.
Tala is asking, do you have any recommendation on the economical embedded hardware that can run model like Qwen 3, Raspberry Pi, or any other similar boards?
Yeah, so Raspberry Pi is, so we use this also internally for testing. And so in general, like I think Raspberry Pi works well. I guess this like one major target of us is also ARM CPUs. So it always depends like how large the model is you want to run, but in general, I think something like a Raspberry Pi works fine. But yeah, in the end, there's many different boards. We also we test a lot of boards. I can't remember like all the different kinds, but as long as they have basically enough memory space in general and bandwidth, they should work fine.
Okay. And but these are CPU only type of processor. Do you see any opportunity for hardware acceleration?
Yeah, for sure. So we also so we have GPUs, of course, but also like special AI accelerators. So in the end, like also like the language models, they only do, or yeah, not only, but a large part of the time is spent in matrix multiplications. And if you can accelerate those, then yeah. So I guess most AI accelerators can do matrix multiplications well, and then it can also be used to accelerate the language model inference.
That's great. Thanks so much, Thomas, for all the availability to answer these many questions and for your great presentation. Thank you so much also to find time to attend today. And thanks again. Time to switch to... Hi, hello. Time to switch to José. Ciao, José. Hope you are doing great. Very good to see you.
Good to see you.
So José Cano is professor from University of Glasgow, and title of his presentation is Accelerating LLMs at the Edge, Hardware and Software Co-Design. José, it's yours, the floor.
Okay, thank you, Danilo. Can you see my screen?
Not yet.
Not yet, okay.
Not yet.
Yeah?
Thank you.
Okay, thank you, Danilo, for inviting me to this event. Thank you, everyone. I'm going to talk about accelerating LLMs at the edge, and this is basically some of the latest work that we have been doing in my group at the University of Glasgow. So, well, this is the 4 points I want to discuss. I want to talk a little bit about how to develop accelerators for LLMs on edge devices and the problems that we can have in this task. Then I will introduce the SECDA methodology and the SECDA LLM toolkit, which are tools that we have developed in my group. Then I will use 2 case studies on which we have been accelerating LLMs at the edge, and I will finish with some conclusions and future work. So first of all, so we know that if we develop specialized accelerators for LLMs, we can make this execution faster and, more importantly, more energy efficient. This is primarily important on edge devices. We also know that FPGAs are more and more available in these edge devices. We can find boards with CPUs, NPUs, and also small FPGAs. The problem is that when we try to develop these accelerators on these devices using embedded FPGAs, well, we found that they have a high development cost. Okay, it was definitely not easy to do. There are 2 reasons for that. The main one is they require high-level synthesis. So just to make it brief, high-level synthesis is the process from which you kind of define an accelerator using a high-level language, for example, System C or C++, instead of using RTL, for example, Verilog or VSDL. And basically, you compile this high-level program or description of your hardware, your accelerator, first into Verilog, and then you synthesize with a process called logic synthesis into an FPGA device. So this process is actually very slow, and you need to repeat it again and again, because once you have an initial design, you want to profile the design, iterate over and over to finally get a design that meets your performance or power budget. In addition to that, if you want to develop an accelerator for a given target device, well, what is the DNN framework that you want to use, right? So you want to integrate it with PyTorch or with TensorFlow or any other available framework. So this is also not trivial and time-consuming. To overcome this problem, basically, we propose 2 parts. First of all, we develop a design methodology called SECDA to efficiently reduce the development time of these FPGA-based accelerators. I will show you how in the next slide. And also, we integrated this methodology with a commonly used framework for LLMs, which is llama.cpp. Okay, starting for the first point, the SECDA methodology. Basically, SECDA stands for System C Enabled Co-Design of DNN Accelerators, and essentially, it's a methodology or an idea that combines cost-effective System C simulation with hardware execution. So to make it simple, if we have here some System C representation of an accelerator, instead of going to the hardware synthesis, map onto the accelerators, and iterate this loop over and over, so this is costly, right? So just for a small device with an FPGA, this can take from minutes to several hours. So the idea is to iterate here, so do simulation all the time. Obviously, the problem is that this simulation needs to be accurate, and ideally, we are going to synthesize on the real hardware device only once at the end, okay? So that's the idea. Instead of multiple hardware synthesis steps, we are going to do a lot of simulation steps and finally, or a few times, just doing the synthesis. Right. On the other hand, I talk about having a DNN framework. Llama.cpp is a pure C++ library that has minimal external dependencies and essentially enables LLM inference with minimal setup and state-of-the-art performance on a wide range of hardware devices. So it actually provides a lot of backends, okay, to run your LLMs on multiple devices. It is very interesting because supports multimodal, custom, and well-known LLMs. And here I'm listing just a few families: Llama, Falcon, GPT, and GenMa. So you can go there and find the latest versions of all these models. One important feature is that it utilizes the GPUF format, and this is basically stands for GPT Generative Unified Format. It's a special format used to represent LLMs, and more importantly, also provides support for different types of quantization, deep quantization actually, ranging from 1.5 to 8 bits. Obviously, we want to deploy LLMs on edge devices, and one of the most important things we want to do is to reduce the size, right? And quantizing deeply the weights and the activations is, well, one of the main techniques to do that. It's open source, Llama CPP, with an active and rapidly growing community. Just to show you an idea, so this is the number of GitHub stars over the last 2 years, and you can see how, well, the number is increasing, right, dramatically. Okay, so we have the methodology, we have the framework. How do we put these two things together? So mixing the two, we created a toolkit called SegDLM, basically a platform for designing custom FPGA-based accelerators for LLMs, instantiates the previous methodology within this Llama CPP framework, and enables fast prototyping and integration of new accelerators with reduced initial setup costs. As I mentioned before, basically doing a lot of simulation instead of real synthesis on hardware. So basically, I'm highlighting here the two parts. At the top, we see in yellow the parts of SegDLMs, how we have an LLM fed into the Llama CPP framework. There is a graph executor that actually reorders the layers in order to execute them efficiently. And the important thing is that we have a backend here, GTML backend, that essentially offloads the computation that you want to accelerate, in this case, in an accelerator that we are going to design. So different operations can be mul, softmax, any type of operation that your model includes that you want to accelerate. There is a context handler that passes operation parameters and metadata to the accelerator driver, who is in charge of communicating the hardware with the framework. Okay. So, well, without going into the details, because this is essentially the methodology I mentioned before, the idea is to be here, right, iterating a lot in simulation, and eventually go here, synthesize the design, and run hardware execution. And obviously here, one of the benefits is that we can measure real, for example, energy consumption, power consumption. Okay, let me show you two case studies that we have developed in our group in order to, make this kind of toolkit work. First, the first one is basically we develop a specialized FPGA-based accelerators for LLM inference, and we wanted to focus on the MATMUL kernel, which in the first model we ran, Tiny Llama, so which is a reduced version of Llama, this MATMUL accounts for 97% of the computation. So pretty much everything is MATMUL operations, okay? So we use a specific type of quantization called block floating point quantization defined in Llama CPP. And particularly, you can have different configurations of this type of quantization. We use the one called Q3K, Q8K configuration. So this basically means that the weights are quantized using initially 3 bits, and then we will do something else in order to recover accuracy, having a final quantization value of 3.5 bits. And the inputs are initially quantized to 8 bits, which is the default quantization for integer value widely used. Finally, applying also some values, 9.1 bits. So that's the idea. So we have a super block that is composed of 256 values. We have our values here, weights, quantized to 3 bits. If we only quantize to 3 bits, we are going to lose a lot of accuracy. So the idea is that we are going to apply to every value a scalar, for example, a block scalar and a super block scalar, in order to recover as much as possible this accuracy loss. Okay, for example, in this value here, we can get a weight multiplied by this block scalar, then the super block scalar. Okay, this is how we actually recover accuracy. Okay, the problem is that once we have our model quantized in this format, well, there is no general purpose processor or compute unit that can execute that. So we need to design our own accelerator. This is the structure of the accelerator design, or the architecture, sorry. So we have a few elements. We have an instruction decoder here that basically loads and decodes opcode-based instruction from the axis stream. Then we have a data mapper that loads weights and input data streams into the respective buffers that are located here. Then we have a scheduler, which is a very important component which orchestrates data movement and control flow. For example, enables styling to increase data reuse as much as possible. And the central point is the superblock vector processor that basically exploits parallelism across superblocks, as the one I showed you before, and also includes format-specific optimizations for this particular type of quantization. As I will show you in the second example, well, this could be also tailored to other types of quantization. So this is the experimental setup. We run this model in this board that contains, a small dual-core ARM CPU plus a small Xilinx FPGA. And well, we run this model, Tiny Llama, which is 1.1 billion parameters. And we basically compare the performance against running 1 or 2 threads of the board. So just to give you some results, this is the comparison, right, between using 1 or 2 threads, and here in these columns, using CPU plus accelerators. Well, as you can see, basically using the accelerator improves dramatically the execution time up to 11x's. for example, 1 seconds per token versus the initial 19.2 seconds. And we also see that, for example, adding more threads doesn't actually improve the performance, and this is because this model is basically memory bound. Okay, so even if we have 4 or 8 cores, the performance running more cores on the CPU wouldn't improve. Just to show you an initial example of how we of the different iterations of this design. This is the initial design, and then simulating and running, we basically exploit the superblock parallelism, and we have version 2, and then improving version 3, and you could even improve this in more. Okay, well, that's the idea, that you keep iterating, simulating most of the time to improve the time. Okay, so for the second case study, well, we observed that actually Llama CPP utilizes a mixed raw floating point quantization scheme across layers. So the idea is that as we profile, essentially, different models can be quantized with different types of quantization. So for example, Tiny Llama, as I showed you before, the Q3K dominates, and this happens also to Mobile Llama. But for example, in GPT-2, most of the weights, actually more than half of the weights, are quantized to 2 bits, and also a quarter of them with 6 bits. Okay. Well, the problem is, how can we run these models? Now we have different types of quantization. Can we build an accelerator that is able to kind of support all of them and eventually switch between formats? And the answer is yes, of course. So basically, this is the structure of the Q3 block that I showed you before. So for the Q2 that we are going to use now, so essentially it's pretty much the same, but because when we quantize to 2 bits, it's more aggressive and we potentially lose more accuracy, we need more kind of scalars and values to multiply in order to recover accuracy. And that's the reason that instead of having one single scalar and a superblock scalar, we have what is called minimums and for both scalars and superblock scalars. Okay, just other numbers to multiply and recover accuracy. So the accelerator for this case is pretty much same as before. So the 3 first elements are the same. So the difference comes in this dynamic superblock processor. So essentially, we should be able to kind of dynamically change if the layer we want to run is quantized to 3 bits or 2 bits. Okay. So in this simple example, we just include one of these units, one of these dynamic superblock processors, but we can scale the design to have 4, 8, 16, or whatever number we can map onto a given FPGA. Given more into the details of the superblock processor, basically, so we have here, the elements, the loader to load the data, different caches, split into different buffers for the different types of data we need to and scalars we need to support. And more importantly, down here, we see how the compute unit actually has a vector engine to do most of the computation, but when we need to apply scalars, the scalars are different for 2 and 3 bits, and we actually have the 2 paths of execution running in parallel. We initially built a unique path, and we were able to choose inside the path itself based on the type, but we realized that actually having the 2 in parallel and choosing at the end which result we want is actually faster. Actually, it was 2 times faster. So let me show you some numbers of execution of this case. So in this case, we run a more powerful device with an ARM CPU with 4 cores and a more powerful FPGA. So basically, these are some resource utilizations of our board. As we can see, I want to highlight that the DSPs, the flip-flops, and the lookup tables, we are using actually low percentages. This means that we can improve this design to get better performance, right? Some specifications about the LLMs: number of Q2 layers, number of Q3 layers, parameters, and size, total size in megabytes. So in this case, well, these are the results that we got. An average speed up of 1.4 compared with not running the models on the accelerator. I just want to mention that this was just an initial design. Obviously, as I mentioned, there is a lot of room to improve here. Well, I also want to highlight that for the GPT-2 model, as you can see, we are getting less improvement. And this is basically because the intensity, the arithmetic intensity of this model is less than the others. Okay, but as I mentioned, a lot of work to do here. Let me provide some conclusions. So accelerating LLMs on resource-constrained edge devices, we know that are becoming more and more important. Many reasons about that: network availability, security and privacy, cost, and so on. There are many reasons. Our SecLLM toolkit improves and eases the development of these specialized FPGA-based accelerators for LLM inference, employing the Llama CPP framework together with our SecDA design methodology. As a case study, we have an initial accelerator to accelerate Tiny Llama, and we see that comparing with the CPU, we accelerate up to 11x, which is significant. And the second case study has motivated the need for having a heterogeneous block floating point quantization support for LLM accelerators, because the models are actually shaped in that way, okay, using different types of quantization for different layers. And as I showed you before, also for the activation. Some points for future work. So obviously this was just an initial work. We are adding support for more VFP areas. We know that some models include 4, 5, or 6 bit quantization, so we also want to support those. We want to expand this SecDLM toolkit as an open source platform. It's not yet open source, but it will be soon, because we are preparing another publication, including more LLMs, more datasets, and more edge devices in the evaluation. We also want to support more types of layers. We know that there are some emerging layers like infinite attention and others that are happening. And of course, the idea is to be flexible to support those new layers. Also, other different types of cores. For example, instead of implementing multiplications, we think of implementing, for example, shifts that are cheaper in terms of computation and obviously power consumption, and support for sparsity. Everything I have shown you until here is dense, and we know that sparsity is also present in many models, and we want to support that. Finally, the automation of the design space exploration, right? So what are the knobs that I should use in order to have the ideal configuration for a given target device? Is something that we are doing now manually, and we want to automate with some type of, even maybe with LLMs too, okay, this automation. Okay, so that was my talk. Thank you for your attention. I'm happy to take any questions.
Thank you so much, Jose. Yeah, I missed it. Okay, you're back. So thanks so much, Jose. Let's see any question. Javier, in the software pipeline, how is the compilation code of these operators done to integrate as a backend in Llama CPP, and how much impact has the heterogeneity with other operators such as softmax that maybe have to run on the CPU?
Well, for the point of basically uploading operations, well, we can have different kind of functions to upload different type of or accelerate different types of computation, right? So Max or any other layer that we may include, right? For the compilation code gen of these operators, well, basically we rely on what Llama CPP provides. The only thing we do here is to actually upload part of the computation to an accelerator instead of running everything in the CPU. So we actually say, okay, this computation. So the backend is going to be that particular accelerator rather than. But we are not actually focused or working on the code gen compilation part.
Okay. And you show that multi-threading for the hardware acceleration doesn't bring too many performance improvements. But is that because of the particular model that you use, the subset of the model that you use, or are there models that could take benefit of multi-threading as far as the neural processing accelerator?
Yeah, absolutely, Danilo. So it depends on the model. So for example, for Tiny Llama and on that particular board, right? So there were no improvements, but for example, in this one, you may have noticed that the improvement in this case is less. And well, there are two reasons. First of all, because we put less effort on designing the accelerator. Second, because we were running 4 cores, right? So it has 4 cores and are much more powerful than the 2 cores of the other board, right? So even if you get one, right, the difference between one of these cores in this Cria board compared with the thing is massive, the difference, right? But it's really, really model dependent.
Yeah, sure. And I don't know, maybe does models do models with reasoning offer more multi-threading opportunity or just more complex?
Well, one of the things that we have been actually been doing in the past, not only with LLMs, but with other models, with paired models in the past with normal CNNs, is that, well, you can always use one of these threads to do computation, right? One of the problems is that sometimes you have the accelerator ready to go, but you don't have the data ready, right? So you could be in the background just preparing this data, pre-processing this data in order to feed the data to the accelerator whenever it's required, right? So yes, so obviously, if you have this kind of idle threads, you can always do something to overlap computation, right? for data preparation.
Thanks, Jose. I will continue with some questions until the time permit, unless I see new questions in the chat. For that, I really encourage the people. So yes, Umran, is any distinction mode between dynamic and static matrix multiplication in case study 1 for orchestration?
Well, the second version is actually an update of the first, right? So initially we were only supporting one type, okay, and there is no dynamism in the sense that you always you don't change dynamically about the type of layer you run, right? And the orchestration basically, or the mapper, right, in which, for example, the tiling that you may apply to a given layer, this is common. This part is common, but it's basically, as I showed you, the core, the superblock processor, what changes, right, from one design to another. We are actually now working on a more advanced core, and instead of supporting 2 types, we support up to 6, right? So we are already supporting this thing now. It's under development.
Jose, there is, I'm not yet familiar with, I just understand that there is an initiative. There is an initiative about microscaling standardization by some company. Are you following that? What's your opinion on that?
To be honest, Danilo, I have heard about that, but I really don't know what the efforts that are being made on that.
Okay. And really, how complex is the effort to support different modes in terms of types, integer and floating point types, given the heterogeneities of these in modern small language models?
Well, there are 2 things here. The first one is that every time you need to choose some options, obviously you need logic to manage that efficiently, right? But I would say that the example that we have now with a new accelerator that supports 4 types is that, well, when you have a very limited fabric to map things, if you want to support different formats, 4, 5, the more formats you support, the more extra logic you need to manage all this, right? So it's really a limitation on the amount of things you can put, right? So especially when you have such a small FPGA, right? But I wouldn't say that the fact of providing the support for different types of quantization is or different data types, more widely speaking, is the problem, right? I would say the challenge is really to make it work, and well, keep in mind that we don't worry about the accuracy, so the accuracy is given to us, and we rely that quantizing these layers to 2 bits and the other 3 to 3 bits, this provides the accuracy that is required, but a given application, right? The challenge is to make it, to fit it inside this small FPGA and make it work efficiently, because at the end, what we care about is, okay, providing 5, 6, or 10 tokens per second, which is basically what we care about.
And in the methodology part of your presentation, clearly you clarified that compilation on the FPGA takes time, so better to do it once than multiple times, so increasing the productivity. How important is that in the light of doing silicon instead of FPGA?
Well, what I presented is we can extend this thing to ASICs, so the methodology would be the same, right? So obviously, the difference would be at the point of fabrication, as you mentioned, right? But all these iterations and simulation steps would be the same, right? But this platform, we haven't tried that, but it would be relatively easy to kind of integrate in an ASIC production pipeline in order to generate a real chip or a real accelerator.
And maybe last quick question, can be extended to Olama as well?
Well, I think yes. It's a matter. We have done this in the past, so we have kind of glue our methodology. Initially, we said that with TensorFlow Lite. Now with Llama CPP, I don't think it would be a great problem to make it work with Olama.
Good. Thanks so much, Jose, for very great presentation. Grateful for your time and also to be patient with all these questions. Thanks so much. And time to give the floor to Tinosh Mohsenin. Hi, Tinosh. Very great to see you attending. I don't see your picture, Tinosh. And don't hear. Okay, yes, now. Yes.
Hi,
Hi,
Danilo.
Tinosh. Glad to see you again. Hope you are doing
Thank you for
great.
inviting.
It's a big pleasure to have you here, Tinosh. And thanks for finding time to attend. I know you were busy with lessons. Your presentation is about E2 Edge GenAI, and I leave the floor to you.
Do you see my screen
Not yet, and
now?
it's coming. Yes, yes.
All right. Well, thank you, everyone. My name is Tinush Mohseni, Associate Professor of Electrical and Computer Engineering and also Computer Science at Johns Hopkins University. And I'm Director of Energy Efficient High Performance Computing Lab, also faculty member of Institute of Assured Autonomy, as well as Data Science AI Institute. So I want to start with a little of the motivation. So at Energy Efficient High Performance Computing Lab, we are developing efficient computing methods that leveraging very novel techniques that cross from different layer of the designs, cross-layer the designs, algorithms, architecture, circuit design, and hardware. So what you're seeing here in this demo, it's our latest work that have been published in this different publications on our embodied edge robotics, which they use variety of models, vision transformers, vision language models, language models, and they bring this intelligence on edge devices, which basically, as you can see here, leg robot, humanoid as well, for basically providing many different, future help with, so that it can be for the embodied edge robotics. Unfortunately, the significant large parameter size of the large language models and limit their usability for these type of devices. So again, what we are basically facing is not necessarily on the kind of these resource compute in constraints devices like these robotics, but we are also seeing these challenges on the large server type of computing. So therefore, on this left side, when you're saying this red plot, which is showing the increasing number of the amount of the memory size of these large models, is completely surpassing with the available memories that is existing on the server type of the platforms. But when we look at the tiny ML or edge type of computing, this gap will be even much significant larger, because these type of edge devices usually provide like a couple of megabytes on the on-chip memory and a couple of gigabytes on the external DRAM memory. So the key solutions here that I'm just talking in my lab and these publications I just mentioned is mainly how we can design these novel algorithms and architecture and transformative solutions that it can bring the computation near the memory. So in order to look at the actual solutions that we are providing, let's just first quickly look at the actual transformer architecture, which my focus for this talk would be. So the transformer architecture, which is showing on the right side, mainly consists of the encoder and decoder. Some of the architectures just only using the decoder, or some of them using only the encoder. But the key thing that is basically existing in these architectures are basically the stack attention layers, as well as the feed-forward layers that you can see in both sets. For the attention layers, they capture the relationship between tokens or image patches, and for feed-forward layer, they learn nonlinear feature transformation after attention output. So the reason I'm just showing these two architectures, because in the next few minutes, I'm going to propose present our solutions for two very recent work. One is MagRib, magnitude and gradient informed pruning for task agnostic large language model, which was published in ASIAN Transaction on Embedded Computing last month, which basically in this solution, we propose a hardware-aware pruning methodology that targeting neurons in the feed-forward layers, And second one, basically I provide this presentation with BitMed VIT, which is a ternary quantized vision transformer for medical AI assistant on the edge, which we just presented in Munich for the IEEE conference in computer-aided design, ICCAD. In this case, we are replacing two basically particular, existing board. One is that we are replacing the multi-head attention layers with multi-query attention layers, and also extremely quantizing the feed-forward layers to 2-bit quantization. And we provide the library codes that it can run on available platforms on the GPUs. So let's just look at a little of the background. So when we're speaking about the model compression reduction techniques, mainly it comes with variety of a lot of different these metrics operations. So for example, for the quantization and extreme quantization, we are talking about only 2-bit or 1-bit representation. Pruning means that we can remove many of these connected layers, sometimes actually the whole row, that's what we are doing. And also structured pruning, which, as I mentioned, so it's not only we are basically reducing, for example, the whole row and the wire connection, and also but introduce a structural sparsity in the execution, so it will simplify the memory patterns. But when we want to apply these type of compression techniques, the very, very first step is that to learn, to understand and determine which layers of these transformers or neural networks have the highest potential to maximize the compression. For example, for our work in large language model, large language transformer-based prunings, we model variety of these popular language model like Llama, 13 billion, 7 billion, GPT-2. As you can see here, the red bars, which show the amount of the parameters that are in the feed-forward networks compared to the orange one, which is self-attention layers, are significantly larger. So usually it's around 40-50% more than self-attention layers. So therefore, kind of it makes sense that if you want to do the pruning, it's better to basically start with these fully connected layers. Similarly, in our BitMed VIT, in the VIT transformer, which is basically, it shows on the left side on the kind of traditional and classical form of the vision transformer, which basically do the embedding, patch embedding, and then followed by the encoder, which requires the attention layers and feed-forward layer. Again, when we look at the bar plots, for the breakdown of the parameters of these vision transformers, so significantly the feed-forward layers parameters are larger compared to the attention layers. So again, our approaches for the extreme bit quantization applied to the feed-forward layer, and that's why basically we're getting a significant reduction into the model size and the performance improvement. So I'm going to go with the next steps one by one. One is, as I mentioned, MAGRIP, magnitude and gradient informed compression for task agnostic large language models, where in this case we are looking at the pruning the neurons in the feed-forward layers, fully connected layers, and particularly with multiple steps. So one is that we are looking at basically measuring the saliency that quantify how important each neuron is, and neurons with low saliency scores are pruned. And then we use two signals. One is at L2 norm for the neurons output, and which basically is a measurement of its magnitude and contribution to variance, and also the Jacobian norm, which basically captures how sensitive the neuron is to changes of its input. And together, basically these two levels approach, it basically shows you this type of kind of two-layer approach that I'm just showing for the MAGRIP, and as I mentioned, the code and the architecture is available. So basically, it starts with it starts with the four main steps, as is kind of showing over here. One is that it starts with the first coarse grain pruning, which is basically identifies that which neurons have the low L2 norms as initial candidates. Second is a fine grain pruning, which refines this basically existing pruned version by using Jacobian norms to remove additional and keeping only truly useful neurons in this architecture. And therefore, at the end, we basically apply a differential binary mask to basically deactivate these kind of unimportant neurons. And that's basically what is left, that at the end, we have just a much more sparse architecture. And then finally we start basically evaluating this. So kind of this slide and the next slide just shows that a lot of our evaluation technology, we started with a couple of so smaller models like a GEMA 7 billion, and then we applied it also with the Llama 8 billion architecture, which basically we trained them on the Wikitext. Basically, we used the trained model that was available, and we applied our MacRib architecture, and we fine-tuned them these prune model using, for example, the available Alpaca data sets, and we perform variety of different, first of all, pruning techniques. Pruning percentages. So, for example, on these 3 plots that you can see here, again, is our results for the perplexity, which is kind of the inverse of the accuracy. So the higher perplexity means the less accurate, versus the percentage pruned or version of these, for example, different models. For example, in the Llama 8 billion or the GEMA 7 billion, as you can see, when basically you have the model, which is, for example, the green one, which is basically trained and also fine-tuned on the Wikitext too. So it's basically, obviously, as it shows that it's basically when the percentage of the pruning goes higher, so the accuracy gets less because the perplexity gets higher. But overall performs well, which makes sense because it's basically is the validation perplexity of the models that was fine-tuned also and trained on the Wikitext. And then we further benchmarked with all existing type of famous kind of benchmarks like the ARC, ARCID, or the, for example, multiple choice questions, Booleans, and as well as the, for example, question answering, which basically were showing that are with, for example, maximum of 30%, which basically our score shows that they're relatively doing very well compared to the non-pruned version. And finally, we deployed our pruned architectures on the Jetson Orin Nano, which is basically on the left shows the power consumption traces when basically you're running the 12 different, basically 12 tokens. So which basically that's what shows. And also on the right side shows that how much our pruned model, basically MacRib architecture, can reduce the models. For example, for the GEMA 2 billion, so it reduces about 5.3 times, and for the GEMA 7 billion, it reduces for 5.6 times. So since it's a little tight talk, but I wanted to squeeze 2 approaches, I'm going to switch to the second work, which is called BitMet-VIT, which is basically we apply the stream quantization with 2-bit on the vision transformer. But as I mentioned, mainly on the feed-forward layers of the encoder architecture of the transformer, along with some architecture changes we're replacing with the multi-head attention layers with multi-query attention. But for this talk, since we are talking about a lot of this extreme quantization, I'm going to just focus on the 2-bit quantization. So for the 2-bit quantization, again, as I mentioned, which I showed it earlier, so the feed-forward layer for this vision transformer also significantly larger than the attention layer. So we focus on the feed-forward layer reduction. And the whole purpose here is that to pack these 2-bit memory reads and write in as basically 16 of these memories, which means that so you're basically 16 times reducing the amount of the data transfer between the memories by packing every 2-bit weight instead of 32-bit weight to these architectures, and therefore this basically kind of showing that our quantization scheme that we are using, we are using the particular available Microsoft BitNet 1.5b framework, and we developed the full libraries for these architectures, and we basically my students wrote the code for the 2-bit weight fragments and all the hardware aware CUDA library codes that it can be available, and we already released it on GitHub to be able to use them on the existing Jetson type of GPUs. So again, this is kind of like shows that the experimental setup for this particular architecture, when we are basically applying this post quantization aware architecture and also multi query attention layers. So we retrain the model, this vision transformer model, through knowledge distillation with basically by keeping the original teacher value and the weights, and distill the knowledge and packing it to this particular student model. And for the final evaluation, we deploy them on the JSON Orin that on the, for example, for the these different modes. And here is the results. So again, for this MED-VIT, which was the original model, versus our BitMet VIT. So we are, which we run both of them on the JSON Orin, we are basically getting 43 times overall model size reduction compared to the baseline, with 22 times latency reduction, which means faster, and 22 times better energy efficiency, and about 19 times gigaops per second throughput improvement, and while keeping the accuracy almost the same with the original MED-VIT architecture. So that's conclude my talk. I hope I could stay on time. So this is actually Pete's pictures. He visited our lab a couple of weeks ago, and we had the pleasure to present for Pete. And I would welcome everyone to come and visit us at Johns Hopkins. I can take questions. Thank you.
Thank you so much, Tinosh. Great presentation. We have a question from Brenda. I might have missed it. Does the pruning process in the first project, which is Magrip, require retraining, refining, training? If so, are there any best practices on retraining with the big or smaller data set?
Yeah, so your question is that are you retraining them?
And I think she asked, yes, if Magrip require retraining, refinement, yeah, due to the pruning techniques you proposed.
Yeah, so basically here we yes, so we do some retraining, yes. So but we use the existing model that is completely trained, like generalized model. We fine tune them, and then basically we use our approach there, which basically again retraining them.
So the approach based on saliency computation about the neurons, is that done during fine-tuning or during the inferences?
During fine-tuning.
During fine-tuning, okay. And then applied in the inferences, right?
Yes.
Okay. So any impact on the accuracy is compensated during the fine-tuning itself?
Yes.
Okay.
So, yeah.
I hope this answer Brenda question, because she was asking also about best practices with big or smaller data set, but I think you clarified that this is happening during fine-tuning, right?
Yes, exactly. And again, we could use much larger models, obviously, but it was taking really long time. So therefore, we started with the smaller models. And again, also our approach is, as I say, is task agnostic, so we can use them both on the edge kind of, resource constraint, this type of robotics, but also on the server type of architectures that significantly can bring down the cost of the inference of these models.
Okay. Thanks so much, Tinos. We are running out of time. I'm really apologize. There is another question. Maybe if you have time to answer in the chat, that would be really nice. Thanks so much for
Sure.
your great presentation and the contribution you brought with Maghrib and Med VIT. We will have time
Thank
to
you very
discuss
much.
more on this
Yeah,
topic.
and the codes are available on the GitHub, so I announced them on LinkedIn, so I can also share with anyone.
That's fantastic. Thanks again, Tinos, and hope to see you soon. Now it's time to switch to Andrea Basso. Ciao, Andrea. Very nice to see you again. You are in great shape, Andrea. So Andrea is from Nito Technology, and his speech is about small elements on resource-constrained platform. And please, Andrea, the floor is yours.
Thank you, Danilo. Thank you, everyone, for inviting me. Today, we're going to review, in fact, what is a bit the baseline, right, for running small language models at the edge. We clearly know what are the advantages, right? We don't have to depend on a cloud infrastructure. Energy, we saw, from the previous talk, how important is energy consumption on these devices that typically are designed for operating in low power. Then there is another big topic related to data privacy. The fact that you run the model locally can really protect the data that you are managing, that you are generating. And of course, latency. It's another very important element. And finally, it's you don't have to depend on a network connection that may be good all the time, but in some rural areas or in some large deployments of devices and sensors may not be as stable as we would like to have. So on one side, again, we have today low power devices that typically are based on ARM architecture, but not only, also RISC-V is emerging, and typically are Cortex-M or Cortex-A architecture, and are again limited in memory, and to have a decent small language model, you need at least one gig, I would say, per billion parameters. You typically have limitation on energy and computational power, and also from a structural perspective, the hardware itself, because the bandwidth of the memory may be an issue. If you have an external accelerator, also the bandwidth that you have between the CPU and the accelerator, all the offloading GPU, CPU are issues. And we heard about technologies and techniques for optimizing. We heard about pruning. We heard about efficient compilation of models. But what we're gonna look at this during this presentation is a bit what is the baseline. So what can we do with the current processors? And I'm gonna refer again to Llama CPP, as Jose did in the previous talk, because that is becoming, I would say, a bit the reference framework for a small language model. Llama, in fact, is another framework, but the backend is still Llama CPP. So I think that we can talk about Llama CPP only. And this is a project that started only 2 years ago, I think in September 2023, driven by Georgi Jergenov from Bulgaria, as an exercise, I would say. And he was working at the same time on a library that is called GGML. That some people say that it's GPT based machine learning. I think that GG stands for the initial of his name and family name. But he had an extreme acceleration in terms of attention and development. Imagine that by last year, backends CUDA, Metal, Vulkan were implemented, as well as quantization Q4 and Q8. And on the right side you see the structure of Llama CPP that is very well organized these days and easy to interact and modify, so that you can easily connect. We saw again from the talk of Jose how easy it is, in fact, to connect an AI accelerator or a GPU into Llama CPP. Just to give you an idea on where we are today, the project has around 90K stars, so really huge attention, and several large companies like Qualcomm and Microsoft actually developed backends for this framework. Qualcomm developed an OpenCL backend, and Microsoft ported its quantization 1.5 bits on BitNet, in fact, on this. And another step, because Llama CPP actually was born as a CPU only framework, because Georgi had in mind to enable people that didn't have GPUs, that didn't have large computation capabilities, to do some generative AI. But this evolved in the last year, adding also the GPU support and AI accelerator NPU support for Llama. And we see there are several optimizations that you can follow. We heard about them in the previous talk, but I'm gonna mainly focus on what is available in terms of software acceleration and hardware acceleration on processors that we see at the edge. So first of all, ARM recently released Clady, that is a library quite optimized for focused on ARM architecture, that gives a significant boost for all the network layer processing, so all the matmult, all the activation computation, and so on. And XNPack, it's a well-known library that is also available in Llama CPP, and integrates several components. In some releases, actually, Clady can be combined with XNPack, so that both they can optimize the processing. These are typically optimization that are done based on the acceleration that the processor provides. And typically accelerations are based on neon, so single instruction multiple data acceleration that may have dot product, may not have that, may have capability of processing FP16, int8, int4, and so accelerating in hardware actually the overall processor. And Helium, that is a new set of instructions that is for Cortex-M vector extension of Cortex-M profiles that is enabling also microcontrollers to do some form of machine learning processing, actually quite sophisticated. And then scalable matrix extensions that is available on some implementation of ARM core. From the software acceleration, mainly there are two categories. Clady and XNPAC really work on the hardware support, and so they accelerate the single layers of the network. Instead, OpenCL, that is well known, it's actually a well-known standard used in graphic, can be really used very efficiently for optimizing the processing by using a CPU with a model that is very similar to what previous talk was presenting, so the notion of context and so on, that we're gonna see in a second. So here is Clady AI that has also a counterpart on OpenCV, and so on computer vision support. The advantage of this environment is the fact that you can really, it's based on the notion of microkernels, so micro elements that optimize the computation based on ARM processors, and you can really select just the C and H files that you plan to include in your project and do the optimization. In general, if you compile all the library and then you use it, then Clady will do a model graph analysis, and so analyzing what are actually the optimal kernel that you can include. So adding quite a bit of flexibility. We were talking about the different performances of a given processor based on the characteristics of the model. Here, there is an analysis, and actually the proper kernel can be used and configured. So there's a selection, and then there is the optimized execution. And then on the other side, OpenCL instead, it is a CPU GPU model, and it's very similar to what you already saw in the previous talk. So there is a notion of context in which you have multiple instances of OpenCL devices. The host application that runs on the CPU is mainly managing the kernel through specific command queues that operate on the hardware acceleration component that also develops the notion of workgroups, so that several components can be grouped together to perform the processing in parallel, as well as when you write actually the different kernels for OpenCL, you can do a lot of optimizations inside the kernel, and also having a precise understanding of what is the model that you are optimizing and what are the memory consumption. XNPAC is again a different approach. As I said, it's in the category of optimization just based on the hardware characteristics of the hardware and covers quite a bit of functions. Very easy to use. Now, just to give you a sense of the comparison of the different the different libraries that today you have available for optimizing processing at GenAI processing at the edge. You see XNPack and Clady AI optimize mainly the functions. Clady AI introduced this notion of optimized micro kernel, and they are both very easy to add. Here, from a programmer perspective, you practically link a library in both cases, and the optimization. For example, Llama CPP takes care of optimizing the code. The advantage with Clady AI, as I was saying before, is that on one side you don't have external dependency, and on the other one you can really just include individual microkernels, so the C and H files, so that you can optimize very precisely your code. OpenCL instead, it's a different story, because in fact mainly you need to program individually all the kernels for the particular device that you're using. And this optimization, the quality of the optimization may change significantly the performances of your implementation, and also independence of the capability of the GPU that you have. In general, these edge devices have a very light GPUs, like the Vivante GPU or the Adreno GPUs, and so the optimization that need to be done here, it's the programmer art to get this running really very efficiently. I want to conclude here. So what I did is actually I took all these tools and tried to apply to five devices. I started with the STM32MP2, in which we used Gemma 3 270 million parameters with quantization Q4 KM. And here, just optimizing using the optimization that we could do on the ARM core, on the 2 ARM core, we're able to get 5 tokens per second. And we are currently exploring, writing actually the individual kernels for the Vivante GPU that is on board. Then the other thing I did, I took an old, 10 years old tablet from Samsung with an Econos 7870 that typically I used just 4 cores at a time, and I used the Thermux here, so I wasn't able to use the GPU. But I was able to reach 12 tokens per second, on CPU only. Raspberry Pi, I didn't run this test, but I got that in literature, reach 20 tokens per second. And then instead on a Cadas Vim3L that has an M-Logic processor with 4 cores, I was able actually to optimize both OpenCL and Clady. And this is a board that is, 40 euros. And I was able to get 15.5 token per second. And then I got an old Jetson Nano. This is the very first one. And optimizing with CUDA here, I had to use CUDA 10.2. I was able, to get only 15 tokens per second. This was a bit, sad as a result. And what I plan to do is actually want to try to put the same model on a smartwatch and see how fast I can go. So this is a TicWatch E3, that's a Qualcomm Snapdragon Wear 4100. That is actually quite fast, I have to say, to see what is the performance that we can reach. And with this, I think I'm done. Thank you.
Thank you so much, Andrea. I'm sorry to be the timekeeper, but the agenda is quite packed. Thanks a lot. I think it was great, your talk. I understood your discussion flow and really where you were going to show the things. Maybe we need to discuss offline. There are a couple of questions from Parmeet and Brenda, so please take your time to address them if you can stay a bit. I'm sorry, but being out of time, I need to switch to the next one. But thanks so much, Andrea, and we will talk later about the performances and the framework that are emerging thanks to your in-depth analysis. Thanks again, Andrea. So the next is now, so we are at the end essentially of the session one. The session one was about optimization and co-design for efficient edge GenAI, and now we enter in the second session, Agentic and Distributed Edge System, and the speaker is Xuyong Zhang, Distributed SLM-based Agentic AI for the Edge. And welcome, Xuyong, and the floor is yours. Hello, Xuyong. Hello.
Can you hear me?
Yes. Yes.
Can you hear me?
Hello, Xuyong. Yes. You don't hear us? You don't hear me?
Can you hear me?
I hear you, yes.
Oh, okay, yeah, sorry. I think there was a fault on my side. All right, so let me begin again. My name is Xuyong Zhang from Nokia Labs, Cambridge, UK, and today I'll be presenting distributed SLM-based Agentic AI for the Edge. Recent trends of LLMs. We've seen a race towards larger and bigger models until year 2023, and we've kind of seen it plateau, more like diminishing because of the diminishing return on the investment, right? And starting from year 24, we've seen a large open source group of open source models that are in the small language model here. So I think everyone can agree on that. The 1 billion to 10 billion range is or give or take, is a good SLM model range here. And this is fundamentally due to a lot of advancements in the model centers. To start off with, more efficient MOE, more efficient KV caching, more efficient attention mechanisms, and in-memory compute, and advancements in knowledge distillation, runtime optimizations, and domain adaptations happening in this scope at the moment. And we've seen a humongous, a large volume of research papers that's being published in the archive with the title of Small Language Models, starting from year 23, 24, and continuing with strong. And maybe we see a lot of Google search trends also resembling the same trend as well. Probably typically because of the research paper that was published in NVIDIA in the middle of year 25. So I just wanted to go over through some of the things regarding the generalized versus the specialized SLMs. So generalized models and specialized models are, I mean, neural network itself, if you have more parameters, the model is able to perform better to a certain point. So for instance, this graph, we have 0.5 parameters and all the way up to 72 parameters. And this is a math Q&A question that we're looking at here. And then it passes, significantly well to a certain point, right? The funny thing is that why don't we look into a specialized model and with lower parameters, and we're focusing on solving a specific task, let's say math, let's say reasoning, let's say other topics. And we're seeing, with less number of parameters and less, we're getting, 20+% of accuracy gains from specialization. And also, we spent some time last year looking into, are we getting the performance gains? What are we paying for the cost with SLMs? And it turns out that we're getting 100 times more efficiency with what we pay if we use the SLM versus the large language model for specific cases. So we're in the era now where these language models are beyond chatbots. So these are becoming more multimodal, vision, audio, and then these models are becoming more capable, meaning that it's able to reason, think, and make actions. And this is coming all over the industry at this point. So how do we perceive this language model from the previous existing version versus the Agentic AI version, right? So if we think about the existing LLMs or SLMs, it was a single shot interaction. So basically you ask a query with a bunch of contexts, and it will reply you it will generate your reply and results, right? Now, in the Agentic AI, the role kind of transformed to be acting as a decision-making on behalf of you. So the endpoint, so the prior version would have to contact you to verify, fix, and then do this iteration over and over. Now the Agentic AI does the partial decision-making on behalf of you. So when you put in the request, it starts reasoning, makes the plans for you, and then it looks at the tools, it looks at the memory, it looks at the environment, and then starts executing the loop. Now, this is where it gets interesting. And the question to why edge is also binds nicely to this looping part, is that in the edge, it's the physical, we're interacting with the physical world, and the changes to the physical world is directly applied to that loop where the environment changes, and then the new decision has to be made based upon that. So, and we can imagine a scenario where you have a vehicle and then it's collecting all of sensors. Next time tick, that sensors all change, the values and context and semantics all change. And then you have to run this in many, many loops to enable to acquire the result or evaluation performance that the user is asked. And then imagine this happening with a cloud API. This won't scale well with gigabytes or terabytes of sensory data that's happening in the real world as of now. So we can kind of agree on that. We have edge AI benefits where latency, privacy, and offline capabilities and cost savings are the major benefits here. And we've also seen drastic shift towards more transformer-friendly architectures being into the market. So we're looking at, we're seeing this floor, and the hardware capabilities are becoming more and more efficient to accelerate the transformer architecture and to meet up to the edge intelligence. Now the question is, are we ready for this agentic AI at the edge at this point? And to some point, I might say yes and no. And then the reason why I'm saying that is, yes, you can have your devices with different MCPs or MCP and quantized models, quantized vector stores or data stores, minimized version of your system running on your platform. But that doesn't necessarily mean that is ready for agentic services. So at the same time, the edge is very fragmented. We all know that, right? There's different hardware capabilities. There's different sensor attached to different entities. Some might be moving, some might be static. They have different functionalities. And we don't have that kind of plane compared to the cloud-based agents where you have a single line of code and that just brings in the model. Single line of code just generates the pipeline, retrieves information, evaluates, and things like that. So it's more fragmented and needs more coordination and more sharing of the distributed memory across different devices. So we're coming up with a neat architecture here where it consists of application control layer, which is the business logic. It takes care of the life cycle of the actual query from end to end. So it translates, plans, adheres to the guardrails, looks at the tools and APIs that this ecosystem can use, and manages that. The model service layer here is very also important part of the architecture, is that because these devices can have multiple models that could perform specific tasks, as I mentioned earlier, with specific models. Maybe it's good at solving problems, but some models are better at reasoning, right? But at the same time, this layer also should take care of model conversions that suit specifically to that hardware architecture. Some architectures have an engine that accelerates the models, which is equipped with, let's say, more powerful compute, like let's say like the Jetson series. Some devices might have bare bone, which needs to be run in a binary format or a C++, very, very low level conversions. So this is where the model is being translated. And also the metastore here on the left side takes care of what the performance of the model has been throughout the system lifecycle. And the data management layer is pretty straightforward. It contains it manages the sensors, data streams, and then the data is neatly crafted into the so that the streams are easily processed by other agents further down the line. And lastly, but not least, the orchestration layer is where it keeps the actual communication and resource and capabilities communicating through a network channel. And we were thinking of deploying this kind of agentic AI system to a fleet of robotic devices, a fleet of camera-enabled devices in the warehouse environment, in a farm environment, or even drones. And I was thinking of actually patient monitoring scenarios, but it turns out if this agent pipeline is more controllable and they have very high rate of success ratio, we could probably implement it into ER robotic machines. So I just wanted to go through a simple implementation detail, how we transform the actual query into actionable plans. Is that it takes the template. This is an example template at top, where it has the goals, plans, and constraints, which will be filled by going through iterations. So the goal is, let's say the user asks the presence of a person in a specific aisle in a warehouse, and then that goes through with neat, careful prompting, and then that is supplemented with resources and available tools within this ecosystem. So more service computing-wise perspective here, where these are the tools, models, and status of each entities within the ecosystem. And that is transformed into the workflow and being deployed in the network. So we wanted to look into the impact of this system, especially from the network perspective, because this is an agent. It's not just a one-time call and finish it, right? And it can use multiple tools and multiple external features. So we came up with a very constraint. We did a experiment on a very configured environment with 3 different scenarios, where the first is without using any tools. So the same question previously, asking if there were any person in the aisles, like this, but was constrained to only use a specific tool. The light tool here, it refers to a single limited visual tools, so very low res single video frame to be used in this pipeline. And lastly but not least, heavy tools, where we enable full resolution up to 10 multiple video frames to be analyzed by vision language models, and vector search for higher results. So the traffic source here mainly is comprised of model call traffic, image and data transfers in between, and intermediate tool calls and metadata exchange. So on the right, we have the scale is logarithmic. We have the node tools approach uses somewhat similar to the lightweight tools, because it turns out that the low res single frame was pretty much not much similar to what it consumes using the database lookup. But on the other hand, we can see a significant growth in the network traffic within, due to using multiple video frames going back and forth, using the model, inferring the model more often. So if we were imagining this was very constrained environment, so we didn't have any loops that would loop forever, because we wanted to see if this is what would happen if this would continue for many hours or many iterations. But this depicts a picture of a single tool pipeline usage would consume this much, and this would we're showcasing this as one of example here. And another simulation that we did was that these edge devices have high heterogeneity, where the compute capabilities are different and loads are different. So we did a simulation where node 1 has the full capability, 2, 3, 4, and the following nodes are less capable. And it turns out that if you have a random allocation scheme, most powerful and most capable devices are underutilized, bringing down the actual latency longer than it should to finish the whole pipeline process. Whereas if you have load aware and capability aware placement or selection strategy, we're able to have the average utilization lower by balancing out the trade-offs. So so far we've been building the Edge pilot, and we believe that by feeding resource and topology aware tools, topologies, and resource into the agentic pipeline enables, and also the cross device coordination and collaboration brings closes the gap to agentic AI being deployed to the edge. Future roadmaps are not bound to, but demos, open source GitHub, and more challenging problems to solve ahead. So if you're interested, please contact. Let's have a chat. Thank you for your time.
Thanks so much, Si-Young. Really, you brought on the table new topics and new contribution. Thanks so much for that. I'm wondering if you can comment a bit, and then there will be a question from Brenda. But let me ask first. You say that one big challenge at the edge is the heterogeneity of the edge devices with respect to the service layer, the orchestration layer. If you could put in simple, what are the challenges for the orchestration layer to cope with a number of edge devices that hopefully will scale up over the time?
So there are a lot of challenges, and I can clearly say that most challenging part of the orchestration part and this agentic AI pipeline is that let's assume that this was a single shot interaction. You can assume that this ends in, let's say, from 5 seconds to it can span up to all the way up to, let's say, 30 seconds, right? But if we are going through iteration phases and we don't have like a clear, if we don't implement, or even if we implement something that cuts off in the middle, it sometimes goes off the limits, and we are having the predictability is a big challenge in this situation. So the orchestration wise, that would be something to keep in mind.
Okay. Which is it also linked to the quality of service or whatever is would be defined the QoS in this case?
Yes, of course. Then there's from the service perspective, we have QoS where the use. Well, our example didn't directly mention like the QoS. So let's say the iteration don't end. I mean, it's if we mention a specific, let's say, accuracy or a specific a KPI for that specific pipeline to reach, then that should also that factors into this problem. Yeah.
And the question from Brenda was to share the results table because maybe it was hard to read the results from the video. So if you could find a way to share this information, that would be great.
All right. Okay.
Or maybe you can quickly zoom on it and quickly comment.
Sure, I could do that.
I don't know if possible.
Or maybe I could take it offline after this call.
Yeah, sure, no problem. Another point, Si-Young, these, I mean, we one of the purposes of all these forums and the working group, the Generative Edge AI working group, is to create a community, especially that sooner will impact hardware at the edge at scale. There are a few brilliant examples of about this is happening, and but obviously we need more, and Also the presentation from Jose Cano was a contribution in that direction. But this service layer in a system architecture, including the orchestration, where do you think these are running? Are running at the edge, on premises, in any new layer, type of device layer, or where? Please comment.
I think I have multiple answers to that, but presumably on both on-premise and on the edge devices, because for a great reason that if the device, if you let's say have to rely on the premise and it generates 10 megabytes of information every split second, and then you have a swarm of, let's say, interconnected drones, robots, and cameras within the vicinity, then that won't balance out even if it's the premise compute. So I think it's I'm looking at this from a virtualized edge perspective, where let's say if we have resources that are very, very constrained and can't afford to run the transformer, then you can have virtual instance running on the premise, if that would make sense.
Thank you so much, Siyang. Your contribution was eye-opening, at least for me. Thanks so much for your time and to be patient to answer the question. That's great. Time to switch to Marcus. Hi, Marcus. Nice to see you. And your presentation is about agent system on the edge, and the floor is yours, Marcus.
Thank you very much. Thank you, Danilo. Yeah, I'm really glad that I can talk a little bit about the multi-agent platforms for the edge, and what we need, and what architecture we need, and what components we need. Only one small sentence about me. I'm Marcus Rüb. I just finished my PhD 3 weeks before, so yeah, this is just a milestone in my personal life. And this is the first time we go out of the stealth startup mode into the light with our startup FaustHub.ai. And yeah, in this circle, I want to talk about the multi-agent platforms for the edge with you. Yeah, I think, and everybody of you knows, that AI agents are an integral part of a holistic AI strategy. So, and all the AI strategies have a lot of layers. For example, what systems does we need? How will we win? So, for example, the peoples with the change management, the governance with the operation models, AI governance, the legal, of course, when you are in Europe, we have some restrictions about the development process. And of course, data management, AI infrastructure, AI ecosystem, the use cases, and so on and so forth. And in this presentation, we want to have a deeper dive into the data technology and the platform technology about the agents and the machine learning ops at all. And yeah, the main idea when it comes to an holistic framework, a platform, and when we want to make edge agents or agents at all, then we need some components. I think the first layer is pretty easy, and one of the most important is, of course, the governance layer we see in the top. So here we need to preserve the observability, the auditability, the testing, debugging, and the monitoring out of the agents which are running in the systems or in the different environments. So we need, okay, is the model drifting or is the data drifting? And does we have problems? Is everything working fine? Or does we get some problems because we have small language models on device or LLMs in the cloud or on device, and they can make some more assurance about the output. Yeah, then when it comes to the edge agent itself, then we have some different components. Of course, we need the input for the agent. This could be, for example, sensor input. When we have a sensor platform, it can be, for example, and prompt or some other data, like other data sources like native data, which is on the controller, or cloud data, which is connected to the cloud and get always, for example, the weather in live weather data. Then, of course, we have the output a little bit. So the actuators, the tools the agent can use or can interact. This could be, for example, a pump when we have really a hardware device, or I don't know, light in a smart home, or yeah, you name it. Then, of course, the agent itself. So this is of course the interaction layer. This is the layer where we plan what we want to do, so the planning components, and of course the SLM or the LLM. And therefore we have the model connection. When we heard a lot of great talks about the small language models which run really on the device, which is pretty interesting and nice. But we can have, for example, a hybrid architecture where we have the LLM in the cloud and connect with the cloud to get the output. Then the platform needs models, so or templates, so we can build the agent, and for example we use this template for a similar use case, or to can change this the purpose of the agents. And then of course we need the interaction layer, or the interaction to other agents or other tools. And this is, I think, when we go to the embodied AI, so AI which is on hardware, like in the edge, like Tiny, for example, it's really important that we thus often will have a mesh of different agents, and therefore we need, for example, A2A or MCP to talk with other agents which are in the room. This can, for example, in swarm of robots, or this could, for example, all the IoT devices in a smart home. This could be, or maybe in an enterprise context where my agent, I don't know, talk with SAP or Workday or whatever to get some informations, and this with agents which comes from third parties, or which I build by myself on, for example, N8N, Kubernetes Studio, Google Agent Space, you name it. Yes, and when we have a deeper dive into the core architecture elements, we always need to have a look, okay, is it scalable, is it secure, is it interoperability for agentic AI? And like I told before, for example, when we look into the governance layer, it must be oversigned the entry agent architecture, including the platform and the agent itself. We need to have defined, for example, governance structures for the third-party agents and custom agents as well. Then, of course, the compliance and security and the operational standards that we say, okay, if we have a drift, please mark, or maybe go into the error mode, or that we can see what is really happening, and that we can afterwards look, okay, why did you make the decision you made? And then when it comes for the agent frameworks and the models, it's really important that we can choose the models what is the best model for this use case. So it always should be a multi-model strategy for SLMs, for LLMs, from the different vendors. It should support the common model connections via cloud platforms or on device, and it should be really open when it comes for different frameworks, and it should be open for third-party agents or agents I built on other frameworks, for example, Langgraph or N8N, or I showed right before. The central role of the cloud-based platform is the scalable agent architecture, where we have the availability of an agent-specific runtime, which is, for example, on the edge device. Then, of course, we need the storage for the data, which can be here, in this case, hybrid, or with a cloud edge use case, or only on the edge. And then, of course, the connectivity, like I told before, with the different agents from the third-party agents. Yeah, when we look at the protocols, I think the most of you will know these two standardized protocols, which are in the moment looking really good that this will get the really new standard when it comes to agents, when it comes to connectivity about LLMs and SLMs. So on the one side, we have the MCP, which is the Model Context Protocol. It's developed as an open standard to let LLMs mount data sources or APIs or tools which can, different sites. When we have, for example, tools on a edge device, this could be really actuators like pumps, like the lights, or whatever you can put on a edge device, or for example, more cloud data or cloud informations, like I talked before, the weather API, which we can call, for example, with MCP. This is really it's a really good standard, which is adapted by the most of the companies, I would say, and it really gets the new standard when it comes to communication for LLMs. Then the A2A agent protocol, it's really fresh, introduced by Google in the beginning of the year. I would say it's not like MCP, it's more for data, for the tools. Agent to agent is really to talk with the agent itself. And therefore, we need an agent card where we can define, okay, my vision, my target for this, or my mission for this agent is to optimize the household energy, for example. And then the agent can talk with another, can say, okay, my mission is this, your mission is this, what for tools do you have, what for tools does I have, and so they can plan together to get to the result. And these two protocols are not working not against each other, they are complementary each other. So I would say we need both in the future. We need the MCP for the tools, for the data, and we need the A2A to calculate between the agents. Yeah, and when we will have a look on what type of agents we should build on such a platform, there are 4 types I often see. So the first type is the single specialized agent. So this is the one agent which works, for example, on our embedded device or on our edge device we developed, which had, for example, when you look at smart agriculture and smart greenhouse, for example, then we say, okay, you have this and this sensor, temperature, humidity, for example, and you need to grow cucumber, and these are your actors. You have a water pump, you have the light, and you can control it. So a really agent only for one purpose. Then we have the embedded agent, which we, as a developer, doesn't often have impact to it from the inside. So these are the third-party agents that will come with the different platforms we will use for, in a company context, for example, our Workaday agent, or when we look, for example, in someday maybe a robot agent which works in our household. Then the third one is the multi-agent orchestration. This is a central orchestrator agent manages several sub-agents. So, for example, in a household, in a smart household, we have one agent which mission is to be the most efficient for this household energy, and then we have the sub-agents, for example, a water pump, or the energy consumption itself, or all the devices we have in the household, and then they can talk each other and can plan the most efficient. And then the last one is the federated agent network. And this is there are really distributed agents which have different missions, which doesn't work most of the time together for one case. They are only working together when they really need. So they are federated, and they doesn't have to do a lot of. The complexity goes from 1 to 2 to 3 to 4. Will be even higher. I think in most cases which are really productive use case, we often see the first or the second type of agents. I'm not often really see multi-agent orchestration in the moment. I think in the next couple of weeks, we will see a lot of more in this field. So yeah, and now I want to introduce you own really short in a small demo, the Faust Hub.ai. So with all this information I showed you before, we want to build a platform which make it easy for you to build really edge agents or agents for the edge. So we built a no-code visual builder where you can drag and drop the different models you need for an agent. Then it will generate automatically C code, which you can, for example, put on your Arduino or on your platform. Everything of this is a modular agent architecture. So we does not only give you the agent builder, we give you the registry, the governance layer, and so on, the communication layer over the agents you can build, and everything should on the target always is the edge and not cloud platforms, which are not so really the edge devices. And therefore, I want to show you really short and small demo how this can look like. So here in the beginning, you see our dashboard of the platform. And when we can, for example, build a new project. And yeah, for this demo, I prepared a little bit something. So we have really basic agent. We have a serial read input. We have the cloud agent block where we can define a name. We can give device key. We can choose a model. We can give you an instruction here. I prepared you a helpful assistant and started every answer with, "Hey, darling." And yeah, we can put in some files when we need this, for example. And yeah, so we can configure our agent. And then as an output, only a serial write. So really, really easy. After we define it, we can download our C code. In the moment, we only support Arduino, which will increase over the time. And then we get a whole Arduino project. Yeah, this project, now we can open in our classical Arduino IDE. And when we uploaded this on our device, in our case, this is an ESP32. I just use for it, and then we get classical code. We can, yeah, I think all of you are really experts in this field. And then we can see, okay, we have a Wi-Fi connection, and we can enter a prompt, for example. Yeah, let him talk a little bit on German. Hallo, wie geht's dir? Hello, how are you? And then we should get an answer. So, "Hey, darling," so it works. Mir geht's gut, danke der Nachfrage. So, I'm well, thank you for asking, and how can I help you? So, yeah. And on this platform, like I showed you, you can really build really easy agents. You can, for example, put some input blocks into your agent. You have some logic blocks you can put in, and so you can build your workflow, your agent as easy as possible. Yes, and furthermore, you have, for example, a device registry where you can put all devices, where you can cluster devices and can say, okay, all this agents type A can talk with each other over A2A, over our platform. And yeah, this is so more or less the main idea about how you can, what is important for an agent framework, and about our startup idea we just launched. So yeah, if you're interested, please go to our homepage, have a look, and yeah, if you have any question, feel free to ask.
Thanks so much, Marcus, also for the interesting demonstrations on Arduino. Really, you passed the message and represented well your technology. I mean, I have a couple of, we have 1 minute left. So just one quick question. Once again, at the edge, we have and we will have even more heterogeneity. So how the agent-to-agent protocol can abstract and through which kind of standardized approach, if any, can abstract the complexity of talking between different edge devices, and how this is handled by your tool.
So yeah, the main idea behind the protocols is to give with the protocol the context, and this is always the most important. Agents and when we build agent, it's force us to have a really good documentation and to give every agent a really clear mission. And with this mission every agent has, and with the documentation of the mission and of the agent and of the tools every agent have, we have the context we can send between the different agent types, and we can so they can choose by themselves, or they can decide, okay, is this, for example, agent A is important for me, agent B, or is agent C more important for me, because I get the context out from the agent cards, and so I can see is this important or not. And this is the main key, I would say, is context, and the really clear documentation of the context.
Thank you so much, Marcus. Unfortunately, the time is over, but we have another question in the chat, so please take your time to address Ilias' question. And I really appreciate the time you spent with us and to present your project. Very, very interesting. Thanks so much. Now, time to switch to Pratik, Craftive AI, Agentic AI in action, and really with you and Yashwant, please show these agents in action. The floor is yours. Thank you.
Thank you. Thanks, Danilo, for the invitation, and appreciate having us here on the call. So very quickly about us, myself and Pratik and Yashwant, we represent Craftify. We both are co-founders. So just a little bit brief about ourselves. We both have collectively experienced 20 plus years in the embedded and edge AI domain, largely across the different edge products and the embedded products. What we've experienced is that developing an embedded software has taken a lot of time. It has been complicated as well as expensive while deploying a model on the edge, particularly in our experiences across different industries, whether it be robotics, drones, AI cameras, automotive. Across these industries, what we've figured out is that every time we deploy a new model, it suffers a data drift issue, it suffers a model drift issues, and when you deploy it in real world condition, it really impacts the model's accuracy. And again, development of a new model from ground up is a costly affair. You can't keep doing it, and because there are so many edge AI accelerator and chip companies, how do we potentially make it easier for any embedded developer to port from one chip to the other? Because again, you don't want to spend 12 to 18 months of effort while developing the software for every new chip that comes up in the market, right? So all of these challenges in the previous experiences that we have faced with a bunch of clients made us to arrive at this junction when we thought that how could we leverage potentially the agentic AI, which is going to be the future, to solve some of these problems on the embedded and the edge AI ecosystem. So with this in mind, last year we came up with this approach ahead of when the generative AI categories were adventing. We came up with our solution of Craftify Orbit, which is a generative AI multi-agentic software development suite that automates the software development for embedded edge and IoT devices. It constitutes of largely two products in the suite. One is Intelligent Pipeline Generator, which automates generation of the hardware optimized code for heterogeneous compute devices, right? Likes of NVIDIA Jetson, Orin, SEMA Model X, Hello, Rockchip, and others. And this Intelligent Edge MLOps, which is a generative AI powered workflow that automates model development, deployment, monitoring, CI/CD pipelines for end-to-end ML pipelines. Collectively, these two products have been showing substantial value to the ecosystem and resulting in a in fast tracking the overall development and reducing the cost by almost 70% with just a push button experience. So this is what we want to showcase in this call and explain you the architecture as well as give you a demo. I'll ask and request my colleague Yashwan to go over to the next slide to present the architecture. Yashwant, I think you can unmute yourself.
Thanks, Pratik. Needless to say, we are building a development platform specifically targeted for Edge AI, IoT, and embedded software development, and deploying ML models on the edge on the heterogeneous compute devices, largely across all the key silicon vendors present in the market. In a silicon agnostic manner is what we excel at. So I present Intelligent Pipeline Generator, one of our flagship product, which focuses on generating end-to-end ML and embedded software application just based on a detailed prompt, detailed spec, either in a PDF form or a detailed prompt in the form of a chat, or either way. So our workflow largely evolved based on the customer's problems, as opposite to many of the other presentations which evolved via research. Primarily, we have a set of 5 agents shown here on the slide, mimicking largely how a typical embedded software team functions in a industrial scenario, starting with the requirement agent, which takes a detailed spec as input, and internally, based on specific use case, specific market, etc. It has different kind of schemas to validate against the input requirements. So requirement agent chats with the user and continues to question the user until it is satisfied with the detailed requirement of. Think of it, if you take example of, let's say, a robotic perception pipeline, where we maybe take a input from a depth camera or a regular camera and do a series of tasks and generate output. So requirement agent ensure that the user has actually provided the required FPS, the kind of model that user want to run, the kind of post processing, ultimately where the data should be going next, what protocols to be used, what kind of performance requirement, etc., etc. And then once the requirement is frozen by requirement agent, it passes it on to architect agent. So depending on the target devices, since we are a development tool and we support large number of devices, at the starting of the workflow, the user is expected to choose one of the heterogeneous high-end compute device which they want to use for the deployment. So the architect agent has several different hardware architecture profiles, and the user is allowed to enter a new profile which the architect agent takes into consideration. The architect agent has a broad understanding of the device architecture. If you take example of NVIDIA Jetson Orin, then the architect agent know that we have a GPU, we have a DLA, we have a PVA, we have a multi-core, about 8 core of ARM A78, and number of peripherals. So the input requirement is broken down into manageable modules such that each particular module maps to one particular compute device present on that heterogeneous chip, and it writes down the pseudocode that needs to be run on that device to get the optimized performing application, and ultimately the detailed documentation is passed on to next agent, which is proposal agent. So the proposal agent acts like somebody who is experienced in implementing a lot of solutions. Typically, a solution that we are building for AGI contains a lot of different plugins or libraries or software modules. Some of them are already present as part of the vendor's library, and some of them needs to be developed manually. The one that are present as library typically requires some kind of configuration to function the way that those modules need to function for the given application, and rest of them have typically a template which must be used. How do we get input data from the sensor, and then how do we call different kind of buffers to really read data efficiently at a very high processing speed? How do we effectively manage the pointers? How do we manage memory uh, across the communication between different architectures? So depending on which particular compute engine is called, a different template exists. And proposal agent calls custom coder, which is our fourth agent. It takes into account the specific template uh, which needs to be used to write code for a given IP block within which was prescribed by architect agent, and writes that code actually. And so think of it, if there are 10 different plugins need to be written to complete an application, custom coder need to write probably 7 custom, and rest 3 were ultimately chosen by proposal agent, and configuration files were generated, all combined together. The complete application is formed by proposal agent and passed to tester agent. Now the tester agent independently generates the test cases based on the solution implementation generated by architect agent, uh, uh, so that each of the module can be tested, and combinedly all of them can be tested at a system level. So tester agent has several different level of testing scenarios, like unit test at individual level, then secondly combining several plugins together and run them in a series to see what kind of output should be expected by that combination, and so on. A lot of times there may be several different types of degradation in performance. For example, if the output uh, is we are seeing output from the optimized embedded pipeline generated by the agentic flow, but accuracy is not good enough. Then tester agents removes plugin one by one and compare that against a Python code that was generated by architect agents input, so that we can effectively really see where is the problem. So yeah, overall workflow is designed to work in a way that it can be AI-led human supported development, as opposite to most of the currently available uh, generative AI powered development, where human takes the lead and AI just helping them. So human defines the overall architecture and AI just helps in filling in specific components. So in that way, we excel specifically in this perspective. We need a lot more embedded intelligence within the agents and a lot more benchmarking for each given device, each type of use cases. So yeah, our workflow currently is in developer preview or pre-production mode, which means it is available for the developers to try out in a very limited sense. And in next couple of months, we are about to release our next version, which will be able to support a diverse range of development workflow use cases, and ultimately different kind of applications for the entire edge market. We are in general horizontal in the nature, that we don't really specialize much into robotics or surveillance or anything else. We function much more at a pipeline level, that for a given pipeline, what kind of optimizations needs to be done depending on what kind of device we are targeting to. Currently, we support several variants of GStreamer, including NVIDIA's DeepStream and NNStreamer, which is widely popular across several different silicon vendors. And in future, we envision to support ROS as a native platform, native C++ development, and of course, hardware optimized libraries instantiated within Python, and several specific chips with their own frameworks as well. I'll go ahead and play a demo of the tool. It will take about 5 minutes or so to give you a really quick overview of how the tool actually feels to use.
Hey everyone, we have new updates to the intelligent pipeline generator. Primarily with this update, the Python coding agent is built right into the tool. What this means is that instead of writing your own Python code separately and then using IPG, we can now create Python programs directly within the tool just by using simple prompts. So let's get started with it. First of all, we'll log into the application, click on the plus sign, and create a new Python project. We'll create this Python project to create our Python application first, and then we'll feed this Python application as input to create the NNStreamer pipelines and deepstream applications. So first, it asks me to select a folder. So I'll select my workspace directory. My workspace directory already has a model file. Now this model file is for image segmentation, and I want to make a Python program that does real-time image segmentation using my laptop's webcam. Now I'll type the prompt to create a Python program for real-time image segmentation using this model. Now this agent is getting started. It has all the tools to analyze the files into this folder, and it can run commands in the terminal, and it can install Python packages, and it can then create the file, and it can run the file as well to show if it is working or not. So first, it has generated a task map for me regarding what it is going to do, and I think it is right. So I'll just type in yes and proceed. So now it wants to create a new Python file in my workspace folder with the name realtime segmentation.py, and now it asks me to run it, and it works. Yeah, this is good enough. Okay, so now I have the Python program. So I have a prerequisite already set to be taken as input to make the NNStreamer pipelines. So let's go ahead and create a new project. This time we'll choose NNStreamer project and click on create. Now NNStreamer project requires two things: a model file which I already have, and it requires the Python file which will be submitted by the tracer. So we'll go and upload the model file first. And meanwhile it's getting uploaded, I'll open the terminal, navigate to my workspace folder where the Python file was created, and run the Python file. Okay. Now Tracer has detected what Python files are involved in this project. So I'll go ahead and click on submit trace data. Now trace data is submitted. That means the Python files involved in this project and the model file has been sent to the server. Now I'll click on generate architecture to analyze and see what this project is about. Now it has given me an architecture document highlighting what model is, what task I'm doing, and the overall block diagram and all the key steps which are needed to do this functionality. Now I will check if NNStreamer already supports such a model or not. And if it doesn't support such a model, I'll need to create a custom decoder plugin for this specific model and task. So let's check it. And it says custom decoder is required for this model. So in order to create a custom plugin, we have a custom plugin generator. So I'll click on the custom plugin generator tab. Now this section has listed that my task is image segmentation, what my model is, and it has already listed the list of installed plugins for an streamer tensor decoder. So I'll just go ahead and select generate plugin. So now what it is doing is creating a sub plugin for tensor decoder. How it works.
Yeah, I think maybe we can move to the next one.
Yeah, sure. Just want to
Hey everyone,
finish it
Python
off.
program.
So ultimately, it generates a GStreamer pipeline, which
Hey everyone,
natively
a GStreamer pipeline. So we first test the function.
So ultimately, it generates a GStreamer pipeline, which natively runs on the supported edge devices. So yeah, overall, typically this task may take at least a couple of days to build the optimized GStreamer pipeline, which with using this tool, we are able to do within a 5 minutes of time spent. Moving to next slide. So currently we support schema.
We are out of time.
Maybe,
Maybe
sorry,
if you have any
yeah.
questions.
Or maybe
Sure.
if you wanted to say concluding remarks and just conclude your session, please.
Sure. So I would just like to conclude that we are building several different tools. First one that we demoed today is focused on building optimized pipeline for edge. There are several other tools which focuses on managing end-to-end ML applications, model development, deployment, observability in the field, and ultimately retraining of the model. And the last tool focus on building optimized edge IoT pipe applications for low-end devices. Overall, with the tool, we are able to see a 70% reduction in development cost, 5x improvement in turnaround time, overall superior quality of the code, and for embedded product developers, it's a push button kind of experience. Would be happy to collaborate with anyone who is into the domain and would like to work with us specifically in automating the overall workflow with embedded agentic AI. That's all.
Sure.
Thanks a lot.
Thanks a lot, Pratik and Yashwant. Really, I'm sorry we ran out of time and, the agenda is packed. But thanks a lot for your presentation and to show also the demo of your tool. I think we need to find another time venue to go maybe also on question and answer. But if you want to share other comments in the chat, please take your time to do so. Thank you so much for your time. And with that, we conclude the session 2, and now we enter in the session 3, Foundations and Toolchains, and time for Matthias, Liquid.ai. Matthias, the floor is yours. Thank you.
Hello, everyone. Can you see my screen, Daniel?
Yeah, I see it. Yeah, sure.
Perfect. Awesome. Yeah. Awesome. So my talk is about LFM2, which stands for Liquid Foundation Models, which is basically how we call our models. Designing the next generation of foundation model architectures for AGI. I'm Matthias Lechner. I'm a CTO and co-founder of Liquid AI. So if you look at all of the device classes where we see like demand for AI, like from a smartphone where we have like a personal assistant to like laptops, again with voice, to factory robots with like a lot of vision and video data processing, to on-prem servers in a way that handle privacy, sensitive data, to cloud services in a way with larger models. We see that the requirements on the compute devices and models is quite diverse. On the cloud, we have like multi-node setups with like a massive amount of memory, but also we expect a high quality if you working with a cloud model. On the other hand, like on a smartphone and so on, we have like much more limitations in terms of memory and latency and memory bandwidth, as well as compute compared to kind of large models. On the laptop, it's quite also different because usually we have more memory available, but the memory bandwidth is often not that much more than a smartphone, for instance. So what we actually need in a way from a foundation model perspective, in a way, is inference-aware architectures in a way that are device specific. For instance, like a architecture that's specifically designed for the low memory available on a smartphone versus like on a laptop. We would need an architecture that is kind of allowed to have more memory, but like is aware of this kind of low memory bandwidth compared to like an H100 GPU and so on. So if that's actually what we need in a way, but if you look what we have currently, it's like the transformer, like all large language models that we see out there, in a way, Llama to Qwen models, to GPDs and so on, based on these transformer architectures. And in terms of quality, it's a very strong architecture. It basically fits any that type of sequential data that you feed into it, but it also comes with costs in terms of memory usage in a way. So what we did as a company is like to look into the design space of architectures in a way, and in a way decompose and create like a way to represent it more efficiently. So including like the attention, but also like all of the alternatives that come out from research, like Mamba, XLSTM, Hyena convolutions, linear attention models, states models, as other linearized features, and so on. So what we did for the company is to kind of parameterize this design space, capture it, and then use that one to do an evolutionary search space, evolutionary search on top of this design space to optimize specifically for each of these device classes that I mentioned before. So to give you an example, like this evolutionary algorithm that we call STAR, how it works in a way, we have like an initial population in a way of an architecture in a way that feeds like input X to Y. And what we do is actually we do an hardware in the loop evaluation to kind of get the number of like the size that it takes up on the device in it. Because with caching it's quite different. Like the actual just the amount of parameters that the model has is often just the indicator of roughly how much memory it consumes. But exactly with caching and a lot of this activation memory and so on, there's a lot of dynamic components as well. KV cache, activation memory, and so on. As well as like we profile how much or how fast this architecture actually runs decode and prefill operations on the device. So in our case, we used the Galaxy S24, so a Qualcomm Qualcomm CPU chip to measure how fast this device runs. So we have like the parameter size, we have the cache, like how much memory it actually uses, as well as like the CPU latency on a Qualcomm edge device in a way, and then we basically prune in a way unpromising candidates, and the promising ones in a way we also train them on like our reference data set in a way and measure like how well actually does this architecture fit the data, because like just having a fast architecture doesn't mean that we actually preserve the quality. So we have like both in terms of memory and latency, some requirements, but also on quality, like, hey, we don't want to sacrifice performance compared to a transformer. So what we did is then basically prune the unsuccessful candidates, like that don't fulfill the speed or perplexity or other requirements in a way, and then use that with a evolutionary algorithm, recombine, mutate architectures in a way. So then we improve kind of on the frontier of like error and versus latency. Here's an example where we have like the first generation of models, and we pick one that has one of the lowest losses, and use that one to generate the second generation of model architecture candidates. Again, optimize here for loss, move further along in the design space of like latency on the y-axis and loss on the x-axis. So this is nice in theory, but also like what we achieved here, to give an example, using a quantized version on like a Galaxy S24, compared to a Llama, compared to a Phi model from Microsoft, and also the Qwen model from Alibaba, we show that the plots on the bottom, you see the throughput, and the plots on top is the latency. So on top is like lower is better, and on the bottom plots, higher is better. And we see that in the orange that LFM2 in a way outperforms model, even like larger models such as the Llama 3.2, which have more parameters, but they're actually slower on the Galaxy phone in a way. Specifically, the decode is a big improvement. And this architecture, although it was optimized in for Galaxy S24, the performance improvements also translates to other, edge devices. So, for instance, here we have a laptop with an AMD Ryzen PC. and also on CPU with a quantized model with 4 bits and 8-bit activations. And we see like very similar because the device classes are very much more related compared to like a cloud GPU in a way. And therefore, for instance, the low memory bandwidth that was optimized for the most that we see on the phone is also present on the laptop. Therefore, we see also like significant advantages compared to standard transformer-based models in a way. So as I mentioned before, these are all like just speed and throughput for pre-fill operations, so prompt processing and decode for the token generation process. But as I mentioned before, like this is nice in a way to have a fast architecture, but what's also important is to have to maintain the quality of a transformer. So we know that transformer is a very proven, in a way, battle-tested architecture, so it fits any kind of data to it. And in this table here, we show that we trained actually 3 different sizes of this LFM2 architecture, like from 350 million parameters, 700 million parameters, and 1.2 billion parameters. And we then evaluated a lot of these standard benchmarks, including MMLU, the multilingual version of MMLU on the bottom, also grade school math, instruction following, and other capabilities. And what it shows really that it outperforms like significantly, for instance, a Llama 3, 1B architecture in a way. Despite having much smaller size of the models, and not just size of the model, but also improved inference latency, but also the quality is really maintained and also like as competitive to kind of transformer models out there. So one thing that I should mention is that this architecture, it's as I mentioned before, custom. It's not based on, as it is. It has some components from transformer that are derived from the architecture search in a way. But it's an open weight model. So we released this model. And so if you're interested in working on Edge AI applications and want to, get access to language models that are like optimized for like speed on the edge, please check it out. It's open weight. You can fine tune it and adapt and see how it goes to your task. We also have like integration with like Llama CPP and other inference frameworks for edge. Also an NPU compatibility. So specifically like with Qualcomm chips and AMD hardware is coming soon. And with some third-party integrations already there basically implemented. So this is a language model, so text in, text out. But we use this backbone, this efficient edge backbone, to train a family of models, not just that one. So on the left, we see that we not just have the 350M, the 700M, the 1.2B, but we also trained the 2.6 billion parameter model and a mixture of expert architecture that has 8 billion total parameters and 1.5 billion active. So that is more like targeted to actually like devices with more memory, but still like low memory bandwidth, as such as a laptop and the AMD devices that I mentioned before. And we're not limited to text only, but we also trained, vision models on top of it. So basically what we do is we added a vision encoder to the language model backbone to kind of generate this, what we call LFM2 VL series, visual language series. That's ideally like for, video processing and other tasks. So this is actually being used in production with some of our customers that have basically like edge video processing with this vision language models. Again, like the 350M with a vision encoder comes to around 450 million parameters. So this is on the bottom up to the 3 billion parameter vision language model that's based on a 2.6B language model backbone. And not just vision, but also audio. So we have a prototype that's still like a lot of improvements going to be happening the next couple of weeks to months. A 1.2 billion parameter audio model that's again optimized for edge. So this is a bit more computationally intensive with like the audio decoding. And this basically allows native, so you don't need to transcribe the audio to text and then to a text-to-speech model afterwards. This model can do everything in once. So you just feed in the audio into the model and it generates tokens and speech out. But as I mentioned before, we expect that there's a lot of updates coming the next couple of months on that audio model. So this is in a way what we did, in a way what we have done so far. But like in the future, we are doubling down on like optimizing for other platforms in a way different, like even like cloud that we're looking. Even though there's edge is a lot of most of the demand at the moment like on edge, but also there's a big demand for cloud that benefit from edge models because the low, the volume in a way. If you have like an application with like a large user base and so on, you actually want to significantly reduce the cost of offloading to the edge, but also like run the edge model on the cloud in a way, in a very large batch regime in a way. And also for modality specific aspects. So what I mentioned before, like the improvements on the audio is like one of the things where we double down again on like really optimizing on the edge the capabilities that we can provide in a way already, like basically just the same quality that we see in cloud models at the moment. We want to really bring to embedded devices with the LFM2 series, we already did the first step in this direction, but like there's a lot more that we going to release over the next couple of months. Yes, this concludes my talk. So please, if you have any questions or follow up, reach out to me or I don't know how much time we still have for the session. But thanks so much.
First of all, Matthias, thanks so much. I think we have still 5 minutes for Q&A, and really your presentation is impressive, and I've been following Liquid.ai for a while, and I have to say that you are doing great performances and developments. Let's check if there are questions for you. How long does it take, and what is the cost, if you can discuss this, of finding a network architecture suited to specific hardware using your genetic search approach? That's a great question.
Yeah, it's a very good question, actually. Yeah. So what we do is we studied extensively the scaling laws. So in a way, like how does with increasing parameter size, in a way, the performance of the model improves. So there's this scaling laws that applies mostly to transformer, but other architectures as well. Basically, like fitting training a couple of models at different parameter sizes, and then basically fitting a regression plot in there to really see, like, okay, like if we train 100 billion parameter model, what quality should we expect from that in a way? And we did this extensively because of the reason, the question that you ask in a way, that training, like let's say a 3 billion parameter model is actually quite expensive. So we cannot use train of a 3 billion parameter for actually doing the architecture search. So what we do instead is we train the models like roughly like hundreds of millions of parameters, so much smaller. But not just one size in a way, but really like multiple sizes, but still at a very small scale, like as I mentioned, for hundreds of million parameters. And then in a way fit a regression plot to see how well this would fit into like a 3 billion, 14 billion and the other parameter regime in a way. And then we extrapolate from there. So basically what we do is like we optimize basically for smaller size. And then once every, in the evolutionary process, once every, 10 iterations or 10 generations, we then test it on a bit of a larger run to make sure that we don't overfit in a way to that very small setup, to make sure that this transfers. But that's how we, we try to keep the cost reasonable to train models. And I think, the amount of actual cost or GPU hours, I think it really depends on how much we want to optimize.
That's great. Matthias, just a question from me instead. I was for a while interested on conversational human-machine interaction, audio basis, and usually a naive approach. An approach is to use speech to text, and then LM model, and then text to speech. While I understood one of your foundational model, especially on audio, does all the three function in once. Can you comment a bit? And also, I wonder if you already bring in one of these models, you will bring reasoning capability.
Yes, that's a good question. That's actually like the audio model. Like we did a lot of research, so that's why it's like the least mature at the moment. Like unfortunately, but like as I mentioned, we'll make a lot of. We're currently doing a lot of improvements on the architecture side. We basically very similar to the vision models in a way, where we just use like a SIGLIP or like a vision transformer in a way to encode in a way the images into like the tokens. For audio is in the input space is very similar in a way. Like just instead of like a vision transformer, it uses I think some FFT based models in a way that in a way convert the speech into like some latent representation that is basically similar to tokens in a way. On the output, we tried a lot of different approaches. Most of it decreased quality a lot. So what we found to be working is interleaving audio with text. So what we do is we predict an audio. First of all, we predict the text, a couple of text tokens, and then we predict the corresponding audio to the text tokens. And the reason we do it, and because we figured out, we tested, if you only predict the audio tokens, the quality degrades a lot. So you need to really let them, in a way, the model needs to think in token space, because most of the pre-training was done in like text token space. So it also needs, in a way, the text tokens are always kind of to ground the audio, to steer the audio in a way. And so basically what we are doing now is like, one of the improvements that we're now doing is to do parallel decoding, to not just doing like sequentially, like interleave, but really like parallel audio text in a way. But as I mentioned before, the text one is very important. So you don't just predict the audio, but concurrently, like in parallel, the audio and the text. And
that's good, Matthias. Obviously, I would have other questions. I hope really you consider as Liquid.ai to be to attend to the other events or be active part of the AGI Foundation community, because I think I perceive that community as your own. So please consider to be active with us. You are doing great. Congratulations. Now, time to switch. Welcome. Time to switch to Parmeet. Parmeet Qualcomm will have a speech about backbone toolchains for GenAI. Thanks, Parmeet, to be here with us today, and the floor is yours. You are muted, Parmeet, please. You are muted. Parmeet, you are muted. You are muted. Okay.
Hey, Danilo.
Hi, Parmeet. Please unmute.
Can you hear me now?
Yes. Yes.
Okay, perfect.
Okay, good. Go ahead.
Yeah. So I'll just start again. Good time of the day, everyone. It's an absolute pleasure listening to all the talks, number of wonderful topics. So I'm going to speak about the backbone tool chains, for generative AI. So when we talk about the generative AI, the very first topic that comes to everyone's minds is about the LLMs, diffusion architectures, in short, the models that the people are running. But the reality is that models are just one piece of the puzzle. The real magic happens when we have the right tool chain, the backbone that is going to enable the compute resources and orchestrate it very intelligently so that the inference happens without compromising the latency and the cost. So in this talk, we are just going to deep dive little bit into how the tool chain should look like, and how the Qualcomm on-prem appliances and the edge appliances are making use of the software stack to provide all the major components. So without any further ado, getting into the crux of the talk here. So we know that we have talked about like what are the catalysts that are driving the AI at the edge. There are a number of trends related to the privacy issues, how the connectivity and the data from the users for the personalization is really important for the adoption of the AI. all of these trends and the catalysts are pushing the AI towards the edge. And there are a number of use cases related to the safety, cameras, physical security, robotics. All of that has been enabled over the last 3 to 4 years at a tremendous pace. So with that in mind, the Qualcomm has the Dragon Wing brand, which has like the number of products, the edge products that are fueling the AI adoption across the enterprises, SMBs, and the large companies at this point of time. But if you look at, it's not just AI. These products has connectivity, compute, different modems, and so on. So on this graph, if you see here, right, you have the devices that are going from simple to the complex, and then going from indoor to the outdoor. So if you look at the complex charter for the indoor, we have the AI on-prem appliance that is really being adopted really well and is getting a lot of traction at this point of time. So in this talk, I'm going to focus a little bit more on the software tool chain that we have for the AI on-prem appliance at this point of time. So if you look at the AI on-prem appliance, what exactly it has? From the hardware perspective, it has the Qualcomm AI 100 Ultra cards, which are actually being deployed on the CSPs at the far end at the cloud as well. So what we are effectively able to do is that you are able to bring in the cloud-grade functionality and the capabilities to the edge in the box being delivered to the end users. With the memory capacity of 128 gigabytes per card, you are able to run LLMs up to 109 billion parameters at scale. And with the software that we are going to discuss and the backbone tool chain, we are able to deliver the complex pipelines like RAG, enable the multi-user and multi-tenancy support, and adapt the solution for the larger enterprises and the SMBs. So we have the Edge AI, and we have the cloud, and we have the on-prem cloud as well. So now in the previous talks, we were also talking about, okay, SLMs are getting adopted, but then there are always certain capabilities for which people do want to go to the cloud as well. So what we have done is that the software stack or the tool chain should be able to have like the hybrid capabilities so that it can do the things on the device or on the prem or the edge. And for certain requirements based on the model complexity or the query complexity, for example, in multi-turn chat, if you're really going into multiple number of turns, you may want to send that query to the cloud as the complexity grows. So this is the software stack or the backbone tool chain that is required almost by anyone for the swift integration and the changing needs of the generative AI models and architectures to meet the use cases that the industry is really looking for. So we will go over the different stack layers of the tool chain and then the different options that are available in certain layers or the capabilities that are required as part of each of those layers. So going bottoms up, on the platform side, the layer 0 and layer 1 are about the operating system and the system software that you need to have. On the operating system, the Linux-based operating systems like CentOS, Red Hat, Ubuntu, all of those are really important because they are going to provide you the scalable enterprise-grade environment for running the AI workloads. On the layer 1 of the system software, you need to have like the accelerator drivers and the container-based easy deployment and the monitoring or the telemetry support of the hardware to ensure that you are able to handle the reliability, accessibility, and the security from your edge deployment as well. Now, layer 0 and layer 1 are focused on the platform side of the things where you are taking care of operating system and the system software. But going one level up in the layer 2, that this is where all the complexity around the AI workloads start coming into the play. Now you need to have like a super solid and adaptable compiler that is able to take different architectures, different models, and then depending upon the user SLOs, should be able to map those networks onto the hardware to get the last bit of performance. And in one of the later slides, we will see what are the different strategies and techniques that are used. You need to have the likes of transformer libraries. This is one example for the transformer-based architectures. But what you want to ensure is that if the model is being trained anywhere on NVIDIA or AMD GPUs, they should be able to just with the single click deployment be able to run on the inference hardware or the accelerator that you are supporting. Super solid profilers and debuggers. And there are so many advanced AI techniques that are coming almost every week, like the speculative decoding, prefix caching. How are you going to adopt all those advanced AI techniques? Your software backbone toolchain has to be capable of doing that. Now, one level above this, you have a layer that deals with the ML frameworks like the PyTorch, Onyx, TensorFlow, which are being used by the ML engineers to create the models. But when the GenAI came into the being, the inference deployment requirements changed a bit from the CV and NLP days. The reason being, because the generative AI queries are not going to have the fixed input and the fixed output. You are going to have the need of having the techniques like continuous batching, supporting multiple queries from the multiple users to efficiently use the hardware. And the runtimes are advanced as well. So we have the Qualcomm AI100 runtime that is integrated well with the VLLM and the GenAI serving tools. From the frameworks perspective, PyTorch, we all know like the models are, if you look at the data, the 75% of the models and the papers that came out last year were from the PyTorch framework. They were using the PyTorch framework to develop their models. So there is clear ask that you should support the PyTorch as natively as possible. On top of all these backbone tool chains, there is a need for the end user to develop the applications. Some of the common use cases like chatbots, generating the content like images and videos, developing the agents and integrating them into your business pipelines, and then supporting the complex use cases like RAG and code generation. You want to have as less friction as possible for the end user to develop those applications. So running the models with the sufficient performance is one of the asks, but then for the adoption across the enterprises so that they start using these edge devices, you need to have a clear, easy way to develop those applications. So what we did in the last 1 year was that we announced the AI Inference Suite that provides the capability to the user to start using these common use cases from the day zero of the deployment. It provides you all the capabilities like OpenAI compatible APIs for content generation, for LLMs, for VLMs, for the embedding generation, indexing, so that you are able to just, even if you want to port your existing applications to the new devices, it makes it really easy for that. So we talked about the current challenges that the users and the enterprises are facing. Looking at the stack, there are so many options that are there at each layer, and the fragmented tooling around that, it really becomes challenging and then creates the friction for the deployment, because for the CIOs and for the people who are going to start the POCs or take the AI to the deployment, they are going to fear that you really need to have big set of expert people who can make use of these complex tools and then start doing some work with the AI. So the customer needs a unified visual ID, that can be used to deploy the application all the way from the cloud to the edge. And the onboarding should be accelerated along with all the observability so that you can make it really easy for all the managers and the MLOps deployment to user personas. So what we did has been that you need to have the integration for the easy deployment, do the Docker registry override for the security and air gap deployments, for the load balancing and the security reasons, do the reverse proxy setup. And the user should be able to have like a single sign-on support for, again, for the privacy and the security reasons as well. And from the deployment architecture perspective, on the cloud, you can have the Kubernetes and shared vector databases and so on, and the lightweight version of the K3s-based deployment and the JSON workflow-based deployment on the Edge AI. Now, in this video, what we are showing here is that with the very easy Langflow-based integration, user is able to take a visual route to create a complex RAG pipeline by just providing the JSON files or visual ID drag and drop based boxes to create the different configurations and then call the queries on the provided documents that will use the RAG pipeline to provide you the answers based on the context that is being provided by those documents. Now, that was the easy part, that where you are providing the ease of use for the application developer. But we discussed about the compiler and the strategies that are required to squeeze that last bit of performance from your hardware. If we look at the AI 100 Ultra card that is being used on this edge on-prem appliance, the architecture of that card is that you have the 4 SoCs, and each SoC has 16 NPUs into it. So there are a total of 64 NPUs on a single card. So it is a tremendously complex process to map your LLMs or other models onto those 64 NPUs. And there are different strategies through which you can map that network onto your hardware. And each strategy is going to have a different pros and has to have its own pros and cons. For example, in the pipeline parallelism, in this example, I have a graph with the 4 layers. So you can create different stages, splitting the graph, say between L2 and L3, and then pipeline those in stages across the different SoCs of the card. If the throughput is the main goal for you, then the pipeline inference really work well. But another strategy could be the tensor slicing or the tensor parallelism, where each layer is sliced across the different SoCs, but then you need to have the communication after each layer, which is multicast nature, across the different SoCs to start working on the next layer. This is going to increase the stress on the communication and the bandwidth. But if latency is the main goal, then in many cases, tensor parallelism really helps. And for certain advanced users, they really want to go hybrid, because in those kind of networks, you may want to use the pipeline and the tensor parallelism together. So for in this example, you have the same pipelining done, creating the stages for the layer 1 and layer 2 and layer 3 and layer 4 separately. But then within the card, you are doing the tensor parallelism across SoCs for each of those layers. So these are the different strategies that are being used, but the good backbone toolchain should be able to hide all these complexities away from the user and then let the user just run the model and still get the best performance out of it. So from the backbone toolchain perspective, it should be easy to use, but no one is going to run it if you are not able to deliver the performance. So the compiler and the strategies that it is going to use is really going to be very critical. Through all this backbone toolchain, what you are able to achieve is that you can support different modalities of input for the different kind of use cases that are using different kind of LLMs and the model architectures to deliver the end business goals that goes all the way from the operations to the facility to the asset management and the different kind of use cases in each of this segment. To wrap up, I would just want to mention that the success of generative AI, especially at the edge, depends on more than just the powerful models. It requires a well-orchestrated tool chain that spans across every layer, all the way from the operating systems to the container orchestration, to the inference serving, and the use cases like the inference suite providers. As we move forward, the building these tool chains is really going to be very important to unlock the full potential of the GenAI across industries and the environments. With that, I will conclude my talk and open to the questions. Thank you.
Thank you, Permit. Really a comprehensive presentation. So, quick question. I cannot afford the cost of the cloud for fine-tuning my LM models. So I can get them from Hugging Face, and then I need to train them, but I mean, the cost and the power consumption of the GPUs burn my office. So is an alternative your on-premises solution for me to move forward?
So Danilo, I missed the first part of the query. There was some lag. So
yeah, let me repeat, Permit. You know, I can download models from Hugging Face, but then to tailor this model on my use cases, I need to fine-tune them or train a bit to fit into my data set. And also, this is a problem that I see from some small, medium enterprises as well.
Yep.
So I cannot afford GPU costs, and I cannot, my energy distribution network cannot afford cannot afford power consumption because these GPUs are really energy greedy. So can I use your setup? I mean, your Qualcomm on-premises architecture. For example, in my home, to fine-tune my model on the use and to fine-tune the L models, the LM models, the edge language models that I need for my use cases on my own premises. Is that affordable in terms of energy consumption and cost?
Yeah, very good question, Danilo. So the TDP for this card, it is 150 watts for a single card. So there are many places where the box has been deployed. Say it is very well suited for, say, deploying it on 7-Eleven or those kind of setups. Now, when it comes to the fine tuning, it depends upon like what kind of fine tuning we want to do and what is the model size, because ultimately it is going to be the memory capacity and the time it is going to take to fine tune on a single card that is going to dictate as well. So if the user is willing to spend some time, then yes, the software stack and the card, it supports the fine tuning as well. As a matter of fact, at the PyTorch conference this year, we demonstrated that capability, that with the AI 100 Ultra cards, you can do the fine tuning. But yes, it is a parameter efficient fine tuning. We are not talking about like the full model fine tuning here. And then performance is dependent upon how many cards your power budget and the costing can support.
Okay, so I refer to, for example, model up to 1-2 billions parameters. Then depend if these are 4 bits, 2 bits, ternary. That's depend. But this is the ballpark. The ballpark that Vijay Janapa already clearly defined in one of his paper, and this is what really maybe we are interested. We cannot afford. I mean, me and some of the people I work with cannot afford a more complex model. And then we heard from Liquid AI, that essentially small language models, hundreds million parameters are enough if well conceived, if well trained, and so on and so forth. So
Yeah.
this is the ballpark. And if you say that this is 150 watt TDP, I mean, a couple of models in my home, my energy distribution network can hold it. Obviously, 4K watts, definitely not.
Yeah.
So that's the case I'm looking at. Then, if deployable in my house, I certainly can be deployable in small premises, certainly.
Yep. Yeah. So the model up to 1 billion parameter size, and the size of data set, which is, depending upon, because the size of data set is going to dictate your time it is going to take for the fine tuning of the model too.
Sure.
And the quality of the model is also dependent on that. So, but from the capability perspective, yes, you can fine tune up to 1 billion parameter model on this card.
Okay, very good, Parmeet. Let me allow to stop your session. I think the contribution was just great, Parmeet, and I think the on-premises LMAI is fundamental in our ecosystem. So thanks to find the time to join us and to speak. It was really great. Thanks. And
Thank you.
time
Thank you
to
so much.
switch. You're welcome. And time to switch to Ashutosh. Hi, Ashutosh.
Hi,
You look
Danilo.
great.
Such a great session this morning.
Thank you so much. It was a team effort, yes. And yeah, you are the last but not the least, obviously. And I'm really eager to hear from you. Edge AI suites. So please, the floor is yours.
Thank you. I am going to share my screen.
Yeah. Not yet.
Should be coming. Okay.
It's coming. Thank you.
All right. You all have had such amazing session this morning. So I'm going to talk about Edge AI Suites, which is Intel's effort to bring a lot of open source components to enable the ecosystem develop more optimized solutions for the edge. If we look at Edge, it spans across so many different verticals, right? Like you have so many different use cases that are powered by Edge AI and are already benefiting from a lot of AI use cases. GenAI especially is still penetrating across a lot of these use cases. There are some use cases we have already started seeing. The real world inference actually becomes very, very important for these kind of use cases, because you have in a lot of those resource constrained, power constrained environments, and even budget constrained. The total cost of ownership becomes much more important when you deploy these solutions than your raw inference performance. And all these breadth of different Edge AI use cases are driving a humongous amount of technological transformation. So what we are doing at Intel to enable the ecosystem. At Intel, we are taking an open edge approach with our open edge platform that brings together software capabilities across the stack, mostly in the open source. It's all available royalty free. There are a few that have slightly different licenses compared to Apache. Bring together on capability to basically enable on Intel hardware. Of course, we are developing primarily within Intel, so it's validated across Intel range of Intel hardware. But it is all these capabilities are available in the open source from a Linux base kit as Edge Microvisor toolkit that you can customize and create into immutable flavors to test your deployment, to test silicon features, to manageability capabilities that bring together the ability to remotely control your devices that you are deploying across in distributed edge locations, to a collection of optimized libraries that enable you to bring your optimized, to develop your optimized Edge AI use cases. On top of this is Edge AI Suites. So the concept of Edge AI Suites is curate the solutions for industry-specific use cases. So this is more of the architecture side or architecture slide of the Open Edge platform and overall Intel's Open Edge approach that brings together the AI edge systems that are Intel Silicon powered, specifically designed edge systems across different use cases, from a few tens of watts to just over 100 watts or a few hundred watts, depending on if you want to include discrete graphics or not. That gets validated across the software stack, software layer, along with the partner solutions to give you some kind of verified reference blueprints for builders to actually build the systems that will meet the KPIs that end customer deployments need. And then on top of that, you have the software ecosystem from Intel optimized libraries to open source components to your proprietary components that you bring together to build your solutions. So as I mentioned, Edge AI Suites encompasses the vertical specific curated applications and components that enable the builders, the solution developers to speed up their solution development. There are currently 4 AI suites available in the open source and more coming. So retail AI suite, manufacturing AI suite, metro AI suite, and robotics AI suite. These have reference example use case implementations that help you understand how you can build optimized solution architecture, optimized application architecture, not just the inference, model inference, right? Like, so when you are building an application, you need business logic, you need a communication between different microservices, you need model management capabilities. How do you bring all those microservices to make it a scalable architecture? And then how do you benchmark those applications, end-to-end application performances on the hardware that you want to deploy it on the edge? And device qualification workflows for your specific targeted workloads so that you can find the right hardware that can meet your KPI needs, whether you want to deploy it in a small Starbucks store to manage maybe 4 camera streams, or you want to deploy in a giant warehouse, there are 60 plus camera streams. What right hardware you want to choose, how do you bring optimized solutions, optimized workflow for those use cases. As I mentioned earlier, there are currently 4 AI suites available. Metro AI Suite, Metro AI Suite that addresses the application development capabilities needed for this smart city type of safety and security type of use cases. For manufacturing, there are a lot of those use cases that bring video analytics workflows, time series workflows, human machine interface workflows, and that you can find some of those sample applications available in the manufacturing AI suite as well. Similarly, for retail, we have a few different type of use cases that bring together vision, GenAI, and other capabilities to deliver some of the solutions for retail, for example, order accuracy or automated self-checkout use cases. And of course, robotics AI suite that brings together not just your traditional SLAM and object detection, other algorithms, or path mapping algorithms, but also workflows for vision language action that brings together your transformer architectures and diffusion architectures flow together for the future of robotics use cases such as imitation learning. Just showcasing some of the little details about what is inside each of these AI suites. As I mentioned in the Open Edge platform introduction slide, there are Edge AI libraries components that are brought together into curated Edge AI suite. So for example, if you look at Retail AI Suite and you look at in the bottom, there are multiple toolchains from the Edge AI libraries that bring together to deliver you the Edge AI suites for retail, and a few different types of sample use cases that are supported that combine visual as well as GenAI capabilities, in some cases even utilizing vision language models, small vision language models that can run on-premise on the devices from core ultra processors to processors that you might have along with your discrete GPUs. The core ultra processors that Intel delivers brings together your CPU, your integrated GPU, as well as NPU capability. So you can take advantage of APIs that are inference APIs that are provided by OpenVINO inference software to take just write code once, and that can be you can deploy across these different acceleration capabilities that are built within the core ultra processor. Similarly, for Metro AI Suite, lots of these components that you can see and the use cases that are being powered, from natural language search to digital avatar to visual Q&A, or to more vision-based traditional use cases like smart intersections, smart parking, that pull together a lot of these AI library tools to help you understand how you can build architecture. Towards the end of the presentation, I will show a brief use case as well. So I'm just going to quickly brush through this so that I have some time for Q&A in the end as well. So similarly, manufacturing AI suite, I had already mentioned some of the time series use cases, visual AI use cases, as well as GenAI use cases that it brings together. And robotics AI suite, a lot of the optimized algorithms along with workflows for any kind of robotic form factor, from traditional industrial robots and controls to AMRs and AGVs to humanoid type of form factors. I'm going to take Metro AI Suite as an example to show you some of these application capabilities. So for example, if you look at some of the sample applications in this particular catalog, you have the smart search that you can use just visual search by searching different snapshots or different clips within a clip or within stored video data. Yeah.
Quick interrupt. We're hearing a lot of noise on your end. I'm not sure.
Okay, so
fixable.
There is some background work going on, so that might be.
Okay, no problem. Just want to let you know.
Okay.
Thanks.
Time check. I think I have like roughly 4 minutes, right?
You have, so let me check. So 5, you have still 7 minutes.
7 minutes. Oh, perfect.
7 minutes.
So, and there's the smart intersection application, smart parking, lighting detection application. There is a re-identification of specific objects, video search and summarization, visual Q&A that bring together GenAI workflows as well. And then you have platform blueprints to basically evaluate your specific platforms that could even bring like sensor fusion type of use cases. here is a quick video that showcases just the smart search based on just writing text and then using video search. So you can see that, and it's all running locally on premise on Core Ultra processors, and you can see what kind of model is being run. These are all optimized and quantized using OpenVINO. I'm going to show you another example that is basically smart intersection use case. This takes advantage of one of the microservices that we have. It's called Scenescape, that brings together multi-sensor integration as well as gives you the ability to add like VLM and GenAI agents to do smart route planning. For example, if you have multiple intersections, you could have these data fed into an agent with visibility into all these intersections that can understand what's going on in those intersections based on the data that's coming from these microservices, and then help with smart route planning. As I was mentioning, a lot of these AI workflows take advantage of our common API for inferencing that is provided by OpenVINO. You can bring your models from any of the more commonly known frameworks that gets optimized with OpenVINO, and it allows you to access any kind of underlying hardware architecture that you want to address, you want to deploy your model on, you want to take advantage of the compute that is available. It also brings together deep learning streamer. It's a video streaming pipeline. So some of the video analytics type of use cases brings together deep learning streamer that you can integrate with GenAI workflows to basically, you can also run vision language models in deep learning streamer pipeline that will basically give you the information that can be published over MQTT to some other dashboard. I will show a quick example of this use case that takes advantage of deep learning streamer as well. And the scene intelligence or Scenescape microservice that I was talking about, you can see the architecture of the scene intelligence service that brings understanding from multiple camera streams, and then you have different communication interfaces that enables you to understand different aspects of the scene and run additional business logic on top of it to build your application. So before I go there, I want to quickly jump to this So I have this application. You can deploy it on-prem, you can deploy it on the cloud. So just for the simplicity, I have deployed it on one of an AWS instance. So you can see it's basically monitoring this traffic scene. And let me turn on the live view. So you have all the cameras, and all the intersection being watched using 4 cameras. And you can create multiple regions to understand what's happening in those regions. You can create tripwires within those regions, and then you can add, say, VLM workloads on top of it. That's watching each of these data that is coming from each of these intersections, and then sends information to your let's say intersection dashboard. So for example, each one specific region saw some kind of a flooding happening, that VLM noticed that there is water logging in that area, and there is no weather effect that's happening. So how does that get notified to your central control room to take a look at it, maybe help with some kind of emergency response if there can be an agentic workflow on top of it that's correlating multiple information from weather, from other factors, and sees that, okay, there is no weather incident happening, there is still water logging in that area. Is there some kind of water line bursting coming in there, and that needs attention from the traffic management, from city management or so. So those kind of applications that you can build utilizing these workflows. So just to close on this, so all these things like applications and AI suites and AI libraries are available to everyone in the community. You can go to the docs.openedgeplatform.intel.com or just scan this QR code. And you can also go to GitHub directly for OpenEdge Platform to basically find all these resources.
Thanks. That's great, Ashutosh. Let's check if there are questions. In the meanwhile, you mentioned, different suites integrated vertically, manufacturing, robotics. Maybe you could comment a bit where you see space for interoperability with third parties, either, depending if these are software solution providers or hardware solution providers, and this type of thing.
Yeah. So from software solution providers, a lot of the like say independent software vendors or software developers would either utilize some of the capabilities directly from say, for example, deep learning streamer for, let's say, video analytics development, or of course, OpenVINO is a very important ingredient that gets utilized across software developers, software providers who would optimize their model, and then that would just run on Intel, run performantly on Intel. And when it comes to contributions, it's all open source. So there are people in the community who also contribute to the development. OpenVINO currently also supports ARM CPUs, so you can run OpenVINO on say Mac, for example, right? And from overall, like there is like it depends on how much community involvement happens from different like ecosystem of hardware solutions. That will because we are primarily developing right now, so it's primarily like enabling all the Intel hardware. But as it picks up more and more, there are a lot of components that are targetedly picked up by many of the community use cases, community users, and of course, Intel's customers as well. For example, some of the manufacturing customers directly integrating one of the software component called Getty that allows you to fine-tune computer vision models so that you can have on-device training, on-device learning of the model as you are deploying it at the edge.
Another question, Ashutosh. Obviously, is perfectly legitimate for Intel to consider OpenVINO as a central runtime framework for Intel hardware. That's obvious. But today we heard about Llama CPP, for example, as another framework, and then there is Ollama, which is based on Llama CPP, and so on. So within the suites you were referring during your presentation, and hoping that my mind is not that much stupid as a question. How central is OpenVINO, and how much space do you see for these alternative frameworks which are getting momentum?
Those are definitely important because a lot of community is developing on those frameworks. For example, PyTorch, right? PyTorch is central. A lot of the models that are developed in PyTorch directly deployed on PyTorch, right? So we were late in developing our upstreaming upstreaming our optimizations to PyTorch, but now we have all the optimizations in PyTorch, so you can basically deploy models directly from PyTorch to any of the integrated compute components that we have on Intel devices. Similarly, these other frameworks like Olama, Llama.cpp. So we are working actively on enabling all these for for the ecosystem to be able to either directly in the OpenVINO backend or directly utilizing upstreaming some of those into the framework. So when you are developing, you can just take that will automatically take advantage of those integrations and then do the deployment. So for example, Windows ML for Windows-based deployments for AI PC use cases that underneath runs OpenVINO for all the Intel PCs. So
that's good. So we are perfectly on time, and I hope Peter will join me soon. Thanks so much, Ashutosh, for your contribution. Really appreciated, and for the
thank you
time
for
you
having
spent
me.
with us. It was really a must-have. Thanks so much, Ashutosh, and we are done, Peter. We are perfectly on time after 4 hours. No breaks.
No breaks. No, that was great. I think wide variety of topics and some really good in-depth presentations and a good example of sort of what's currently state of the art here for generative edge AI and agentic edge AI. So pretty cool
and
stuff.
We have
and then we have a whole
actors.
Yes, I was going to say we have a whole set of talks tomorrow too. Of course, people should tune in for that same time, same channel.
Yeah.
Well, any insights from you? Any surprises? Anything that kind of caught your eye? Is like,
I liked quite much all the presentation, and I think the mixed contribution, industries, small industries, big industries, and university is just amazing. I am excited by Liquid.ai. I think these guys are great, but all the contributors today did an awesome job. I mean, I appreciated all the contributions, especially from hearing, the big industry are very important, and I think I'm learning a lot from them. I tend to prefer, the young guys and the startups, and it was great.
Yeah, no, I think it was good. It was good and good diversity. And I see there's a lot of folks on the chat, a lot of questions, which you appreciate. And I know there's some people that are staying up till 3 something in the morning. And again, from kind of time zones that are a bit far away. And, maybe next time we'll try to figure out a way to do maybe one morning, one evening thing to kind of balance it out a little bit. But really appreciate the questions too. I saw there were a lot of good questions coming in. And also on YouTube, this will be on YouTube. And so you can also post comments and questions up there, and we'll try to get to them as soon as we can as well. So, and on LinkedIn as well. So just keep questions coming. But yeah, and thank you, Rosina, for orchestrating all of the slides and pictures and all that good stuff as we went through
Thank
this.
you, Rosina.
Yeah, fantastic. Okay, well, I guess we will do this all again tomorrow morning.
Yeah, stay with us tomorrow.
All right. Bye-bye.